we are not allowed to like publish it, but we can send you the.
Oh, amazing.
Yeah.
Perfect.
Just after the workshop, send to someone in Andalite. Send email, you know.
Okay.
Yeah.
Yeah, thank you.
I just sent you the 5 videos. Okay. Yeah. I don't need any slides for my introduction. It's going to be very short. Oh, those. If they didn't submit slides, then no, I don't have. They're going to come individually. Oh, very short presentations. Is there an HDMI up here if they want to use their own laptop? No. Okay.
There's no HDMI.
No, so all of the slides I'm going to be having.
That won't work. Won't work because
It won't work.
no, it won't work because I have PDF with videos, and no matter what you try to do, it won't work unless it's minus.
What format you say you have?
I have PDF with external videos, just embedded in PDF, but you have anything but Linux and PDF PC.
2:30, okay, so you can. I give you, I try to give you a USB stick. Yeah, no. I'll send you his email address.
Yeah, soon for no slides for me. All right, good morning, everyone. Welcome to day 7 of the AAAI 2024 conference. Thank you for showing up. I know it's a little early. A lot of us have been here for a while, so I appreciate you coming out this morning. I think we have a pretty exciting workshop today. We've got a bunch of exciting invited speakers. We've got some contributed talks. We also have contributed posters. We've set up the poster boards outside, so those of you who have posters can put those up at any time. There'll be time over lunch, but anytime you want to hang out outside and look at the posters, you'll be able to. Every poster presentation also will have a brief chance to talk, to give a high level overview. As with most of the week, we've had a number of last minute cancellations. Thank you, Canada Immigration. As someone who is about to become a Canadian citizen, I have gone through the entire back and forth with them, and it can be frustrating. But thank you all for coming here and getting visas. A couple of our main organizers were actually not able to make it because of various visa problems. So Tempeh and I are subbing in today. But really, Rick did most of the organizing. So we'll thank him later. But I think I want to give up the rest of my time actually to our first invited speaker, Maria. With that, I don't know what you're talking about.
I can say, don't worry.
Okay. Well, I'll ask Maria, what would you do if you had 10, 1,000, or 10,000 robots? All right. And with that, I'll hand it over. Thank you, Maria.
Start with it. Let me see. Right, together. Oh, magic. Okay, let me try to find the location. Okay, so I'm trying not necessarily to answer the question, but sometimes I just like to ask questions so we can think about, right? And the idea here is really, depending on the number of robots you have, you may need to use very different methods for, let's see if we can get this to work, sorry. Oops. Okay, so what are the key things I'm going to cover? Again, do some kind of broad exploration on systems or multi-robot systems, again, from very few robots to 1,000 robots. And you try, hopefully, by the end, you can try to think about, do we really need that many robots? I don't know, but again, I like to always to kind of pose some questions. And can the algorithm really scale up when you have 1,000 robots or not? And the last example I'm going to talk about is, if we have 1,000 robots, how do we know they're going to work fine? So can we come up with some ways of estimating some of the properties? Let's see, so I try to see if this moves. So I kind of start with a very old, more historical perspective. As far as I know, the first project they had like 100 robots. In fact, I think they were 100 or 203, was a DARPA project. It was a number of years ago. This is a picture that shows the robots, and it's kind of interesting. It was in 2004, and they had most of the robots were the active media AmigoBot, who were not really doing anything, and there were 6 active media pioneers. They were doing a little bit more. They didn't really do much. It was a demonstration done for DARPA, and as far as I know, again, the first time with so many robots all together, at least they could kind of move. Not doing much useful, but at least move. And if you do robotics, you kind of know having so many robots work at the same time is just a big, complicated process. The figure at the bottom is the kilobots. Many of you have seen it. They come from Harvard University. They're very, very small. And again, they've developed up to 1,000 robots. They're really tiny. They're like, they have 3 legs. They move very, very slowly. But again, just to kind of cover a little bit the spectrum of what has been done. Let's see if sorry. So there are a lot of applications. I'm not going to go through any of those, but those are just a few pictures showing, a lot of robots. You can think of robots in warehouses, in construction, or outdoor areas. You can also think about a lot of robots in the lab where people are trying to figure out what can I do. Or you can think even about people, because, in some sense, you can think about people moving in crowds as kind of robots. Let's see, this is a bit, sorry. This is kind of slow in advancing. Sorry. Come on. Oops. Oops, sorry. Oops. Okay. So we start, again, I start quickly. Oops, lost the video here. Oops, oh, I don't see here. Okay, I can look at there. It requires creative organization. Okay, so we can start looking at the, a few robots. And then, when you have a few robots, in general, you expect each robot to have something to do. And so the question is, how do we allocate tasks to the robots? Do we need a central controller, or can we do in different ways? And do we have any guarantee on the ability to produce quality solutions? Will the algorithm scale? Again, I tend to ask questions, not necessarily provide answers, just because I think those are important things to kind of think about. Let's see if this works. So I'm not going to read this. Everybody in the multi-robot community kind of knows there is this taxonomy by Brian Gerke and Maya Matarik a number of years ago, in which they kind of define all the robots depending on they can do a single task or multitask, or the task requires a single robot, multi-robots, and are the assignments done instantaneously, or there is some kind of time extended so you can do planning. So this is kind of a standard taxonomy. I'll bring up briefly that we extended the taxonomy because I was very interested in tasks that have temporal constraints and precedence constraints. And so again, we kind of extended to include again this kind of additional constraints. And just to kind of give a very quick idea of what the issues are. So you need to create some kind of objectives for your robots. It could be minimize the time to finish the last task, or minimize the path that they have to follow. You have some constraints, and the constraints, again, can be absolute, like start time, finish time, and maybe time window, so you may have extra time. Can be ordering constraints, could be precedence constraints, could be synchronization constraints. Again, number of constraints. And the figure down here shows, again, you can have constraints, so you can think about kind of a graph with task and the order of constraints. And you can think about the standard way people show tasks, early start time, later start time, extended expected duration in a scheduling community. Again, so this is the kind of things we're interested in doing. And a simple example here, you can have like a surveillance task, and I want to tell the task you have to do a specific task within some kind of time window for a period of time, and then you can watch another place and you can check critical areas. And I'll show here a short video. Let me see if I can get this started now. Let's see. Can you start the video?
This video depicts the allocation and execution of 12 tasks by 3 turtlebots using prioritized iterated auction. The split screens show videos shot with the robot's cameras, and the static image show allocations of tasks to robots. The colors in the figures encode precedence constraints. Red precedes blue, blue precedes green, and green precedes yellow. All the other tasks in turquoise are free of precedence constraints. Tasks are shown as circles and robots as squares. Robots' assignments represented as paths coincide with their colors. The tasks here are visits to waypoints, and once there, the robots turn around to take a video of the location.
Okay, so, So this kind of gives you an idea. Of course, it's done in the evening when there were no other students running around in the building. So it's kind of desert. They were trying to avoid the usual problems you all know we have when, I don't know why people sometimes are so annoying. Like, why do they live in building? They should get out. Let the robots take care of. Let's see if okay. So this again, just to give you a very simple idea. Now, in some cases, you may need different kind of robots. They have different capabilities. And early on, there's not been much work on heterogeneous robots. There is some more coming up here. And I have an example here, which is kind of, oops, sorry. Let's see if I can get this. Sorry, this click. Come on, go back. Sorry. So this is from the old RoboCup rescue simulation. Let's see, there's supposed to be a video here. There's a short video here. I don't know, I can click on it. Okay, perfect. Yeah, this again, if you've done, this is the RoboCup rescue simulation. This shows a bunch of things moving. Of course, they are robots. They are all kind of simulated agents and have police, ambulances, fire trucks, and all the green dots there are people, and they're going to die unless they're rescued. And then you start seeing the top of the city. This, by the way, is a very cool map of Paris because there is a big river in the middle. And you see the area on the top is getting darker, it's getting fire. And so in part because there's a river in between, there are only a few bridges. So everybody seems to be on the south side, and nobody really is up there, and you can see, I mean, this keeps on going. And so the fire takes over and can take over and cover the entire city, right? So the idea here, there are different kind of agents. So there are different agents, but really they don't work much together. The fire trucks go on their own and the ambulances go on their own. But again, it's one of the examples in which there are, again, different types of agents. And I can show quickly, let's see if I can get to the next page. There are two videos here, sorry. Yeah, you can do the one on the top. Again, we're just showing that if there is no coordination at all, this workshop is on coordination. So there's no coordination. You see the robots, the fire truck, everybody goes around and the city slowly becomes darker and darker and gets burned. And let it go, it's almost done. So a big part of the city gets burned because the way the simulation is done, unless you really contain a fire quickly, you don't have enough fire trucks to contain it, right? So not a very good outcome. The one at the bottom, there is coordination between the fire trucks. So they really try to go after the same fire instead of being all randomly, you know, each one running and figure out what to do. And we'll see there's still some fire that is going to go on. But by the time the simulation ends, there is much less fire. So again, this is just a very simple example of how doing some coordination can help. Again, even if you are not really cooperating strictly between different kind of agents. Moving on, let's see. So now I kind of bring in simulation crowds of people, could be also crowds of robots. We never have enough robots to make a crowd of robots. So, you know, typically we tend to look at people, and you have people that have to move in a crowd and potentially maybe, you know, fire alarm here, let's run out of the door. What happens, right? So that's the kind of issues we are kind of interested in looking at. And you can see, you know, in general, people, unless there is, again, an alarm situation, people don't really rush much and they're kind of more moving in a kind of more orderly way. Still, rarely, like even when we cross the street, there are other people, rarely we run into each other, right? Somehow we have the ability to move around a little bit so everybody gets to the other side without too many problems. And the question is, can we come up with an algorithm to do this? And let me go to the next page. Oops. Okay, so basically, so the method we develop, we work on, you have multiple agents, they have a start location, each of them has a goal. I mean, again, think about people when you move around in general, we have a destination we're trying to go through, and we're trying to get them to reach the goal as quickly as possible. So each one try to get there as fast as possible without, you know, colliding with other agents, and assuming that all the agents have a very limited sensing range and have no communication. So again, the issue is, can we kind of implicitly collaborate by not running into each other, but with no communication? And I just show a quick example. So there are two videos here, sorry, when you get them started. I think you have to start one at a time. So, no, start both together. So on the right side, the Orca. Orca is a system being developed a number of years ago, mostly for moving characters in games to avoid collisions. And we do exactly the same examples. And you can kind of see the difference. Because Orca, each robot decides, you know, the direction and then gets told which velocity to use. So they tend to stick more to the direction than kind of merge. And that's our approach. And we give you a very quick idea. Oops. Let's see. So the idea here, again, I'm just going very high level here, right? So we have a reward systems. We have a number of actions. So each agent select an action to do, and the actions are the directions of motions. Then we call Orca. Orca gets this, which kind of the velocity that the agent would like to use, and return another velocity, which is a velocity that doesn't cause any collision, so it could be different. And then we kind of move, and they kind of one of the key ideas here is how the reward is computed. And it's kind of two components. So typically, you get rewarded because you get to the goal. But if you get to the goal, you're kind of greedy, right? You can step over people because I want to get there first, right? So we introduce this term called politeness. And so you get also some kind of reward for being polite, which means either you stop or you take a step backwards. And we can show that, in fact, this helps a lot. Let's see if I can. Okay, if you can start. Okay. We see again the difference. So with ARC again, you know, the door here is not very wide if we have to run out. Oh, there's nobody coming in, but still, right? It's lots of congestion there. Right? And only a few people at a time can make it out. If you start the other one. Again, you see the politeness here, some robots back up, and by backing up, you kind of free up more of the space. I mean, there's still some confusion, but not as much. So again, this is kind of the general idea. So some kind of cooperation, implicit in a sense, often helps in situation in which, again, and you have no communication, nothing else, okay? Again, I'm going through different things. Oops, let me go back one. Just again, to give sort of a broad view. Now, let's get to talk swarm robotics. You know, the word swarm is in the title of the workshop, so we have to tackle it, right? And let's just try to see what swarm robotics, you have many robots, simple, could be almost disposable. And you need tasks that can be decomposed. So if you have 1,000 workers instead of only one, how do you decompose a task so they don't run into each other? And in general, we assume no explicit communication. So just, oops, sorry, oops, this moves faster. Let me go back one more step. Come on. Sorry. Okay, so there's a short video here on the side, also the ants. If I like motion, right? We always like motion. So, oops, no, okay, this, yeah, see the ants, how nice they move, right? And you can see the simulation on the right side. This is some 1,000 robots. This is done with the Argos simulator, where you can have 1,000 of robots. And you say, well, what are they doing? Well, they kind of look like ants, sort of, right? That they're trying to bring stuff to the nest. So this is, again, when you look at very large scale, this is kind of things we're going to see, right? We're not going to see, you know, super smart robots doing complicated things. Okay, so let me go to the next. Let's see. Yeah. Again, this is just a sort of a view of the simulation you get from Argos, which have the nest, which is a dark area, and you have lots of stuff, and some are the robots, some is the food, and then you have lights. I mean, this again is a simple way of modeling the nest place. You have lights, and if you have physical robots, very easy to do light detection, and then they go there, and they think that's a place where they can rest. We're done it. Oh, sorry, this is always moving when I don't want, sorry. So we've done things with real robots, and it's very crude. I don't show any videos, it's very, very slow. And so they're kind of turtle bots. We added some sort of gripper in front. It's not really grip, it's like two sticks. They come out, they have light sensor. We put a bright light source. Food here is boxes, cardboard boxes. Maybe that's what robots like. But again, we try to use the algorithm we develop also with the physical robots. And we have some experimental results, again, just to show that this is the real robotics and not just the simulation stuff. Okay, so we try many different algorithms, and again, I'm just trying to go just some of the general ideas. Did I miss some slides? Sorry, make sure, sorry. No, okay, no, okay, perfect, yes. So we can measure the performance. The performance, you know, the robots are foraging, so they're finding food, finding stuff, right? So we tried again, this is just a kind of a graph that shows different algorithms, and you see the algorithm shown on the bottom line, and the algorithm either use a task decomposition, I'll talk in a minute, or they do random motion, do multi-armed bandit problems, they do epsilon greedy, and we're just trying to show the performance. The performance is the number of blocks collected. So typically, again, we measure the performance depending how good are the robots at picking up the food, and how things change depending on the size of the swarm. So here we got up to 1,000 robots. And so you can see that, in fact, of course, the number of objects grows up the more robots you have, but in general, not linearly, because the more robots, the more run into each other, and so there are more collisions and other issues. So again, just to give you a general idea. Oops. So one of the really interesting ideas in the swarm robotics is the idea of emergent self-organization. So what happens, and we just show here kind of simple-minded idea on the side. So if you increase the number of robots, typically the increase in performance goes up linearly with the number of robots. And again, there may be some kind of not exactly linear, maybe sublinear because of collisions or other things. One thing that happens often, and I don't think there's any really fully good explanation why it happens and how to make it to happen, is when you have enough robots, sometimes the performance that they have when interacting is larger than what you would expect, right? So the straight line here is just a linear increase. And the curved line shows if the robots, when you use the robots there, and they kind of interact with each other. And exactly why this happens is not fully clear. I mean, I know there are a number of tiers, I'm not going to much details, but this is one of the reasons why looking at swarms, very large swarms, is kind of interesting way of increasing performance. Again, some of the ideas here are very similar to what happens with parallel computing, right? If you run something on one processor, you get one speed. Few processors in general have a nice speed up, but then you put thousands and thousands of processors and you don't have the same speed up because there are some other issues. And the interesting thing here is, despite the fact many more, instead of having more problems because of interactions, you get some positive results. So, which is a kind of interesting issue. Okay, so another sort of small idea here is, can we try to take inspiration from ants? I mean, ants is one of the many type of insects that people tend to imitate or use, you know, in computer science for optimization. And so can we start to look at how insects or ants work and try to do some kind of more real-time adaptation? So I'll tell you here, this is kind of recent work, just give you a sort of intuition. So what you like to do, you know, in general, if you use genetic algorithms, you kind of run the algorithm for a while until you find your solution. But if you're trying to if you have the robots and they're out there and you want to start the genetic algorithm, the robots, it takes a long time. So what they're trying to do is see, can we run a genetic algorithm for a short period of time and try to get some interesting results quickly. And so the idea here, again, this is kind of the description, we try to have to update the genetic algorithm in real time. And how is this updated? So we have a bunch of parameters, so like velocity and other things that the robots do. And now say every time a robot comes close to another robot, they can share the fitness function. I am more fit than you. You want my parameters? Take them. Right? So that's kind of the general idea. And fit here means I found more food, right? Because fitness here is measuring that. And so then the other robots, again, get my parameters, and hopefully my parameters are better because I got better results. It's really no guarantee because it really depends. You know, I was in a very area rich of food, so I was lucky, I got lots of stuff. Now we get in a bad area. He was stuck in a bad area, didn't have much results, takes my parameters. Doesn't mean they really will work. But again, the idea is to try to see whether this will help, right? Again, this is kind of the general idea. And we combine again with some kind of strategies or local motions that the robot will do. And again, so, and I show, I'm not going to go, for interest of time, I'm not going to go in a lot of details, but this kind of high level figure here, but it's a little hard to, each robot has chromosome. Again, the numbers are value for parameters. We have like 4 parameters. And then between, you have a generation and you kind of interact with the others. Then in between, you can kind of look at the situations and you can kind of decide what to do. Again, this some, depending what you encounter, what happened. And then you go to the next generation. And so you keep on doing to different generations and updating your parameters. But what you do in between, also the length, how long you do the training with one generation before the next, depending on the environment. I mean, there are a lot of other factors that come into the picture. Now I'll show you some results. Let me see, just to give you a quick idea. And again, I'll just show a couple of them. So this is kind of a random environment, which is shown, this is running WeBots. And it's shown up there. So you create food in random locations, you create your robots. And then here we compare a number of algorithms. I kind of wrote here what the algorithms are. And then we compare the number of objects retrieved per agent with, here the population is kind of small. We go from 5 to 15. And so what you see here that our algorithm is called ADAPT-GA because it's an adaptive genetic algorithms, does better than the others But as the population increases, the performance goes down a little bit. And so, we haven't really done full analysis, but for all the algorithms, so it's kind of interesting, right? You expect to be able, now this is the number of objects per agent, right? So not the total number of objects you collect. And then what you show here on the right side, this is kind of the fitness of individual robots in the team. So you have an idea, some have the fitness that goes up a lot and some doesn't go up much. And this is kind of the path that they follow, again, just to have an idea of where they move. And again, we've done for different environments. We've done for the power law environment, kind of similar. And we've done for urban environment in which there are bigger obstacles, like there are buildings or so, and so it's a little bit different. And again, you kind of see the same things what happens. So now to get to the last piece. So again, so far I'm just trying to give some ideas of different things. Having many robots can help, but can also hurt. The kind of things that they do. If you have lots of robots are different than if you have very more complex tasks, because in general, again, the swarm robot is very good at finding stuff, which there are a lot of real tasks, but it's not very good at doing other things. So now one of the questions that we ask ourselves is, if I have lots of robots, how do I know? And I have to figure how many robots do I need for a task? I have this convention center has to be cleaned because, I don't know, the AAAI attendees somehow leave around a lot of junk or whatever, right? Somebody has to go around and clean it. And say, I have my company, I have my robots, they will come. And he say, okay, you have 2 hours of time, do it. How many robots will I bring? How do I know, right? So again, we're trying to get some sense. Can we assess upfront, have rough estimates of how many we need without having to run a lot of simulations? So again, this I'm going again to. So again, we can try with the real robots and, have some ideas, but it costs a lot. You can do full simulation. Also, it's messy. You can do some kind of models, which typically assume steady state. And what we do a discrete model based on random walks on graph, and we try to do direct computation of some of the properties. Here again, I'll give you a quick overview. So first we create a kind of a graph models, and in which, sorry, I think I missed one. For some reason, I always miss one slide. Sorry. So we do a random walk using a Markov chain model. We represent the space with parallelograms, because if you have triangles, you can move in each directions, and the distances in each directions are the same. So the other people have done the same thing here, right? So that's kind of the way we model. And we use either random walk, or in general use correlated random walk, in which, for people who are not use it, you do random walk, but you tend to stick with some higher probability to the direction you are moving, instead of moving completely randomly. And we got into a wall, then you bounce back. So this is kind of, and what is interesting in estimating, there are other properties. The main one we're looking for is what is called the first passage time or hitting time, which is the average time for the first visit to a node by a set of random robots, right? So if I want to see what's the average time it takes to reach the nest by one robot, that's again, is called the hitting time. And again, we model the space. We have the nest in the middle. We have some kind of limited visibility area. And so here I give just a quick hint on the magic that goes underneath. Again, I'm not getting into details. I'm keeping track of time here. So have some kind of the probability of moving from one node to another node. And then I have the nest, which has absorbing nodes. And so I kind of write a partition matrix, which has the transient state with the absorbing states and the transitions. When I have this matrix, I can, with some computation, I can compute the closed form expression for the mean and the variance of the hitting time. Again, I didn't want to go through all the derivation here. Now, once I have this closed form expression, I can compute very quickly using GMRes, which is one of the many algorithms used for fast computation. And what I'm showing here, again, without telling you exactly what the computation is, depending on the size of the arena, the matrix that represents all the space is huge, but the time it takes to compute is very, very short. For a 30 by 30 is 0.05 seconds, and even 300 by 300 is 25 seconds. Even the matrix is gigantic, but its matrix is a very sparse matrix. So again, we just show we can very quickly do computation on this model and come up with estimates. And how good does it estimate? Here, I'm just showing a simple example here. Suppose that, again, you need to know how many robots you need to have 80% probability that one robot reaches a nest within 500 steps on this size of arena. Again, so you can figure how many you want, right? And here we tried running the program with many different number of robots, right? If I have one robot, up to 500 robots, and then we want 80% the probability, so we can draw this line there, and we have an idea of is about 80% probability, right? So the idea here again is in very simple way I can compute with many robots what those distributions are, and then I can give you an answer. And this is just kind of the beginning of this work. We're hoping to be able to compute different things. So just to wrap things up, so kind of went through multiple kind of robots. They're controlling different ways, the different tasks, and really there are a lot of differences depending on the number of robots and the tasks. And we kind of again look at tasks with precedence, temporal constraints. We look at heterogeneous robot in search and rescue, motion in the crowd, swarms of thousands of robots doing foraging, and robots that adapt to the environment, and kind of propose a way to estimate some properties that will really be helpful without having to run the large simulations. And of course, I couldn't do this work without my students and collaborators. I put their faces here. Thank you for listening. Oh, sorry.
And the way we have this scheduled is there'll be time for questions and answers with Maria and Aaron afterwards. So we're going to ask Maria to, and we'll just keep, okay, we've got time for questions. So now that I'm a little less flustered, Maria Gini is a AAAI fellow, an ACM fellow. She's been the president of IFAMAS and done lots of cool things, including working a lot with CRAW. I know her, so I just assumed everyone else did. Oh, by the way, I'm Matt Taylor. I'm from the University of Alberta. Hi, if you don't know me. So I guess while we're stalling, I had a question. You had the example of warehouse robots. Where are all our other multi-robot systems? Is it the perception? Is it just commercial interest haven't developed? Why aren't there more multi-robot systems?
Well, I think that's reality, right? People talk a lot about swarm robotics in particular, right? The swarms do gazillions of things. I haven't seen any single deployment of swarm robots, right? I mean, just to be honest, I don't know if anybody here does swarm robots. The warehouse clearly is a very good application. Search and rescue, I think there are a number of people that talk about and potentially would be a good place, but I haven't seen anybody except, a few cases. So, but I think, some areas, I don't want to offend anyone, but let's say VR, virtual reality, there's a lot of hype. I mean, there are some results coming out, right? But it's been around for a long time. So, I look at swarm robotics, these very large things, for the future. They're not practical today. We don't really know exactly what to do, but I think it's important to start studying them because I think fundamentally, the notion that in nature you can have very simple things like ants build this gigantic, the termite gigantic nests. I mean, tells us something, right? So again, but you're right. I don't see any real application except warehouses where you do things in a slightly different way. Yeah, sure. Yeah.
First of all, thank you for the great talk. So one of the questions which I have is like one of the thing which you had in your broad like modeling a multi-agent was a politeness factor, which you modeled as a separate factor.
Yeah.
What do you think, like one of the things which I foresee is like that is very hand designed for a particular thing and it's not very robust. Do you think those kind of like social characteristics or social phenomena can be leveraged through large language model when designing a reward?
Good question. Now, of course, everything you do, I didn't mention LLMs, but everything you do requires a large language models, absolutely. I mean, I was at the AAAI conference last week, lots of panels, I've heard a lot of things. So, no, I think, my understanding, and again, there are lots of robot experts here, so large language models are coming into robotics, right? Because they're not only for language, you can learn other things, but I haven't seen a lot of work yet. I mean, many people talk, again, maybe I offend somebody who's done work here, right? And just be careful. They're coming into the robotics field. I haven't seen much yet. So, of course, they will kind of change things, but I don't know exactly how. And again, if anybody has done work with LLM and robotics, it would be kind of nice to know about, because again, it's just starting. Good question. Thanks. Yes, yes.
I did think your polite robots were amazing.
Yeah, yeah.
I could actually hear the Canadian, each of them saying, sorry, sorry, sorry.
Are the Canadian polite?
Yes.
The US, sorry, don't want to offend. I don't think they're very polite, but I don't know. Italians, I don't know. I mean, I'm Italian, so I think, well, Italian, well, I don't know. Anyway.
Well, I'm Canadian, and I try to be polite, but anyway, thank you for your talk. And so, I've taken an interest in the plot where there was a population size in the x-axis and the average performance in the y-axis, and there was the emergence of self-organization coming out. I think there was that graph. But so I'm curious though. I think the self-organization wouldn't just depend on the population size. So would there be? What do you think are the other factors that may be needed in order to come up with some form of self-organization?
I don't know. As far as I know, it's still a little bit of mystery. Why? And people observe, right? Because you collect the data and you say, wow, this grows up faster than I was expecting. But understand exactly why. I mean, somehow it's the interactions of the robots, right? The interactions are not necessarily running into each other, but maybe, I see you already there picking up a piece of food. I don't go there. You're not going to fight and I go somewhere else. But exactly what happens, I've seen a few people that try to have a theory, but I don't know there's much theory. I think it's a very good topic for people, anybody interested in diving into, right? Try to do, theoretical study if possible, or some kind of empirical studies, and try to understand more what happens. We have seen it happening again in a lot of simulations, and many other people have done the same. So, good question. I don't know how to do it, but if you come up with a good idea, maybe you get a good paper at AAAI, right?
Yeah. Thank you for your opinion.
So,
Sure. Yeah. Thanks. Yeah.
You quick question or okay?
yeah, I have a question.
Sure. Yeah.
Go ahead.
So this might be completely unrelated, but I see a lot of similarities to the dynamical systems theory of mind, and looking at the emergence. I wonder, does any of that cognitive stuff flow through to your studies of swarm robotics?
I haven't really seen anyone using that. So maybe there are some people doing. No, I don't. But yeah, good point. Yeah, thank you.
Thank you, Maria. All right. Next up, we have Aaron Corville, founding member of Mila, but most of you probably know him from the deep learning textbook that you've probably either read or feel guilty about not reading yet.
Thanks very much. And thanks for the invitation. So I guess I consider myself actually a bit of a deep learning generalist. And so this is maybe a bit of a departure for me. That this is something we've been actually working on for quite some time. And it'll be I'm kind of used to having the security blanket of being able to control my own slides. So this will be a little bit of a challenge for me, but let's see how it goes. Can I actually use this? Oh, it's on my, can I use this?
I tried.
Okay.
Doesn't fit.
It doesn't fit. Oh, I see. Yeah. Sorry about the technical details. Right, so I guess maybe I can talk a little bit now. So this is a method which the original title was Q-value shaping. The paper is titled LOCA, Learning with Opponent Q-Learning Awareness. So this is very much inspired by methods like LOLA from Jacob Forster's lab at Oxford. Well, actually, at the time of Lola, it was just him as first author, and later he's been really developing a lot of this kind of work. And we'll get into in a moment what exactly the details are here, but generally speaking, these are methods that are based in reinforcement learning, trying to solve social dilemmas. And the reason why I think this is really interesting is because, as we'll see when the slides come up, I got interested in this in kind of a roundabout way. We were playing with a game called Diplomacy for a while. And this is back before the meta really took over that field. But what we saw in there was something really interesting, which is even though, so for you that aren't familiar with this game, it's a complicated, basically a war game where it's centered around World War I with like 7 powers. And ultimately it's a zero-sum game. You're trying to win this game. But in the process of trying to do well in this game, in the process of trying to do well in this game, you're also trying to. Does it work? Oh, perfect. Thanks. You're in the. I'll finish my story. In the process of doing well in this game, what you're trying to do is actually cooperate with other people, right? Because you need to negotiate. The game is structured such that you have to kind of make alliances. And one of the interesting things we saw here when we were starting to play this game and trying reinforcement learning agents with this game is if we use human data, we saw lots of examples of cooperation and implicit kind of almost communication. Even though we were playing a version of the game that doesn't have communication, they were actually using their moves as a way of signaling between players. We let an RL agent try to play this game, and it got rid of all of that. It didn't want to cooperate, didn't want to communicate with the other agents. And so, I mean, there's a longer story here, but it really got me down this path of isn't it interesting that these algorithms, even the ones that we think are relatively sophisticated in the RL space, have this real fundamental flaw, and it's essentially how they approach the world that they're training in. And so that led us to in a long path to this kind of work that we're in right now, which is to say applying reinforcement learning to social dilemmas. So when I say a social dilemma, what I have written here is a type of decision problem where each player's myopic efforts to maximize their own benefit leads to a less favorable outcome compared to when all parties cooperate. And this is really the kind of structure of games and problems that I'm particularly interested in, because these are general sum games. It's a particular category of general sum games, but which is to say, it's not zero sum, right? Like it's not your win is my loss, your loss is my win. It's something else where there's a category of possibilities where we both sort of win. And the classic example of this kind of social dilemma is the prisoner's dilemma here. So in this case, we have a prisoner A and a prisoner B. And prisoner A cannot have a choice, right? So this is the case where they're both sort of, imagine, arrested and in two different interrogation rooms, and they both have a simultaneous choice that they can't observe the other person's choice, and the choice is between confess or cooperate and remain silent, which is another way we describe that as to defect, because you're defecting against the other prisoner. So these two have presumably done some sort of crime together, and they're trying to negotiate. And the sad thing is, in this case, at least the way it works out in the game theory, is that here we see we can get, if they both confess, they both go to jail for 5 years. If say A remains silent while B confesses, A remains silent while B confesses, A goes to jail for 20 years and B gets off scot-free, right? Like he's basically ratted out his partner. If they both manage to remain silent, then they both only get 1 year in jail, which is kind of the best social outcome. Of course, the tragedy in the prisoner's dilemma is that both players confessing is the dominating strategy. Because no matter what the other one does, you'll just confess. It's better for you to confess. So it's a very robust phenomenon that you'll just confess or defect, in other words. Now the situation gets a little bit different if we think about an iterated version of this game. So we're just playing this game iteratively for ever, essentially, or a discounted variant on ever. And in this kind of scenario where you're playing over and over again, something else comes into play, which is you can start to do a tit for tat strategy, right? So tit for tat is basically you cooperate in the first iteration of this game, and then from then on, you just play what the other player did at the last time step, right? This has the benefit of being a Nash equilibrium, and it plays well against itself. It has a lot of nice other properties, but generally speaking, it's a pretty effective strategy. So we would like to get a learning agent capable of learning these kinds of strategies. Yeah. Oh, wait. Oops, sorry. I'm just. got something messed up with the structure of this thing. Those guys used to say something. I don't know why that went away, but anyway, there's a reason for them being there. And the thing that I guess this is the point I was building to when it came to diplomacy is when I was looking at diplomacy and starting to think about these kinds of problems, we can look at iterated prisoner's dilemma as being a kind of a very special case thing that we won't, most of us hopefully will not find ourselves in that kind of a context. But the truth is these kind of general sum dynamics are everywhere. And I found myself kind of just seeing them everywhere when we looked around, right? So in a business negotiation or any kind of deal making, right, you do not have the same interests exactly as the person you're making a deal with. But in many cases, you guys are better off to negotiate some kind of a settlement and move forward with that than you are to just ignore the deal, right? It is not a zero-sum interaction, right? Another case is just driving home, right? Everybody who's stuck in traffic wants to get home quickly, but the reality is that you don't want to also crash each other. So there's a kind of general sum dynamic there as well, right? When if that turns out the best solution is for you both just to take your turns at different points in time along the way. Lane merging is another classic problem that actually we have with autonomous vehicles right now, because they're not able to negotiate that lane merger very easily because they lack a sense of embodiment of the other drivers on the road. And finally, just at a larger scale, we have these kinds of issues of policy negotiations writ large, right, from country to country, even within a country between different factions. These can be seen as kind of a general sum problem, because again, it's the same sort of dynamics that we have at a large scale for business. We can view climate change and negotiations around climate change as being very similar to a game theoretic idea like tragedy of the commons, right? If I'm a particular country, I benefit most from being able to go ahead and pollute as much as I want while everyone else does the responsible thing. That's the cheapest, easiest solution for me, and it gets a good outcome. So what we're interested in doing is learning these kinds of dynamics. And why learn these dynamics? Why not just sort of rely on the game theory we have and to promote strategies that we know of already? Well, it's because the world is complex, right? We're not going to be able to just hand design strategies for a complex world. And so the hope here is that we can leverage RL, and the sort of deep RL in particular, to bootstrap up complex solutions to these complex tasks, and solutions that are complex, not just complex, but are able to actually get to social solutions. Now, this is a long way from where we are right now. Where we are right now in this case is a game like this. So this is one step more complex than iterated prisoner's dilemma, but this is really kind of the state of the art in this field. We have things we're working towards, like there's a melting pot challenge, but nobody's really applied the kinds of methods we're considering here, which are pure learning methods, onto those kinds of settings yet. So we're working on it, but this is kind of where we've gotten to, which is, humbling in a sense, but this is where we are. So the coin game is essentially the same kinds of dynamics we have with iterated prisoner's dilemma. The only difference is now it's kind of embedded within a wider state, right? So we have two players, red and blue, and we have a coin. Now the coin is either going to belong to player red or player blue. And in this case, it's a player red coin. So if player red gets the coin, he gets 1 point, right? Now as soon as the coin gets removed from the game, another coin appears. Of course, this is the iterated part of this game. And now they can both go for it if they want, or we can just let the player blue take it since this is a blue coin. Player red here decides he's going to defect, and he's going to go and take that coin. And by doing so, he still gets a point. So you get a point no matter what color coin you take. But if your coin is taken by the other player, you lose 2 points. So that's the dynamic, right? And so now you can choose. You can either take, you can do more of a cooperative strategy, taking only your color coin, or you can play an always defect strategy where you're just taking everybody's coin. Now, this is the coin game. And if we try to train an RL agent on this kind of a game, we see an interesting dynamic. This is the same thing that happens in the case of something even simpler, like the iterated prisoner's dilemma. The reinforcement learning agent fundamentally assumes a stationary environment. So when you put them in a self-play scenario, both agents are assuming that the other one isn't going to evolve through training. And if you're starting, especially if you're starting with a random agent that's not very smart, what's going to happen is you're just going, oh, the agent's playing randomly. Best thing I can do is just defect, right? Grab all the coins I can. And so they're both kind of myopically going down that path while training. And where do you end up? You end up with two agents that are always going to defect. And this is kind of, there's a really, what I think is a really interesting kind of coordination problem in the learning pathway themselves. Because what we want are agents that learn to play strategies that are not necessarily exploitable, but are capable of cooperating. But it's not what we get when we start with naive RL. And by naive RL, I don't mean like really simple strategies necessarily. It just means that this is a fundamental understanding of how we characterize RL. So can we do better than this? Well, the answer is yes, we can. We can actually apply opponent shaping, like I mentioned before. And this is really work that's come out of Jacob Forrester's group. And the idea behind opponent shaping, roughly speaking, is that agents can shape their opponents, right? Through the course of training, agents can actually adapt their own behavior to shape the behavior of their opponents. Now, there's a lot that goes into this, and we can discuss this a little bit later, but this is the basic idea. So here's Lola. This is kind of the original opponent shaping work that I know of. So the basic idea is that an agent assumes that its opponent is a naive learning agent. This is the case of Lola, and it can simulate updates of the opponent's gradient with respect to the opponent parameters. So here we have, if I can, does this? No, you don't see that. Okay, well, anyway, I'm just going to point here. We have the expected returns of the agent here, and it of course depends on both the policy parameters of itself and the policy parameters of the opponent, right? Because the opponent is determining a large part of the environment for this agent. And the question is can we actually adapt our performance in order to shape the performance of the opponent? And the way Lola does this is it actually projects the opponent's update into the future. So it's basically looking at how the opponent's going to change into the future, incorporates that in the model update, and then does an update with respect to this. And that kind of projection into the future of the opponent is sufficient to allow you to do that kind of shaping. Now, Lola's essentially a first attempt at this, and there are a few limitations. This is good. There's a few limitations with this. One, it assumes access to the opponent's policies parameters while training. Now, certain people make a big deal about this particular weakness. I think this is a really interesting thing to discuss. Personally, I actually don't view this as a particular tragic flaw. If you think from the point of view that what we want out of this is an agent capable of behaving reasonably in the world, this kind of an issue isn't going to be that big a deal, I think. As long as you can deploy into the world an agent that does something reasonable like a tit-for-tat strategy. You have also, it has other problems too. Specifically, and the one I'm going to go into in more detail is that it's expensive. It's computationally expensive. To actually build the computation graph and then backprop through it is expensive. And what we're interested in is building algorithms that are capable of scaling up beyond just things like the coin game. So this is going to be something that we're going to try to improve upon with our work. There's been quite a few actual follow-on works to Lola. The one that we found particularly interesting is this POLA work, and this is the one we're mainly going to compare against, because in our experiments, it's actually the one that's most competitive to the method that we're going to talk about in a second. And it's basically just the same thing as Lola, only we're adding like this proximal penalty, right? Which is just the KL divergence between the old policy parameters and the new policy parameters. And they're comparing this in the space of the probability distribution over actions spaces, right? So this is basically the only difference between POLA and original Lola, but we found it actually makes a big difference in terms of performance. And so this is going to be our comparison. Again, limitations, essentially a subset of the limitations of Lola. We have to assume access to the opponent's policy parameters, and it requires this big computation graph, which we then have to differentiate through, which can be very expensive. And we'll go more into that in a little bit. So our method, which we call learning with opponent Q-learning awareness, basically goes with a key observation, which is that your reward as an agent depends on the opponent's policy and vice versa. So this isn't particularly novel. This is the same underlying assumptions underlying Lola, but we're going to use them in a bit of a different way. say, for example, we have a trajectory here. So we start off in state 0. The agent takes action A0, the opponent takes action B0, and then agent 1, or the agent gets reward R1, the opponent gets reward R2, and then you advance to state 1, et cetera, et cetera. And we, of course, have a probability distribution over this, which depends on both the agent policy and the opponent policy, as well as the initial distribution over states. Okay, given that, what we can assume is when we optimize the expected returns of the agent, there is an explicit dependency on the value function and the opponent's policy. So if we consider the opponent rather than the agent, we consider the opponent's value function, there's an explicit dependency on the parameters of the agent's policy. Right, so this is basically what we're going to leverage. And the way we're going to do it is through kind of a two-step process. The first thing we're going to do is run out a Monte Carlo estimation, because it's important to realize, like, if we just learn a Q function, this is going to have its own parameters, right? And we break that dependence on the policy of the agent itself. If we learn a Q function for the opponent, we can't just update the parameters of the agent. And so we're going to do this Monte Carlo rollout, and that's going to allow us to make the dependency on the parameters explicit, right? And that's essentially what we're seeing here. We can actually build an explicit, and so this Monte Carlo rollout is with this Q hat. So this is basically an approximation. It's an unbiased approximation, but it is high variance. It's an approximation of the Q function here. And the other thing that we're going to do, which I actually think is a really clever idea, this is something my student came up with, is who's the first author on this paper, Milad, is we're going to approximate. So this is only an internal approximation, right? This is an internal approximation that the agent does on behalf of the opponent's policy. So rather than actually use the learned behavior, the learned policy of the opponent, we're going to approximate the policy of the opponent via this softmax. Right, so it's basically a similar kind of transformation that's used in SAC, but rather than make it kind of a target, here we're actually we're constraining the function to be that. And now this allows us to have the opponent's policy directly a function of its Q function, and then we can backprop through that. Right, and so just one thing to point out here, that thing in red, we're actually using the true Q function for the part that we're not differentiating through. That's the true Q function. So everything off our Markov rollout that appears in the normalizer of our softmax here, that is actually using the true function. So in that way, we're not so different from Lola, right? We're actually using the true model. We could think about using a different model where we learn that Q function, but that's what we're doing for now. So this is basically the idea. That this is now in an actor-critic update formulation. So we're not going to worry about the details here, but the important part is that term 1 underlined here, that term is basically your standard actor-critic update that you'd get in any kind of a scenario. And the term 2 is the opponent shaping term that comes from that last thing that we looked at, where we can actually approximate that gradient directly through that softmax. Sorry, approximate the policy through the softmax on the Q function, we backpropagate through that, and we end up with this dependency on the parameters of our theta 1, right? So that's because, and we get that because, if I back up, that there's a dependency on the policy of the opponent, player 2 here, on the parameters of theta 1, because there's a dependency, because there's this dependency on the Q function of player 2 on the policy of player 1, right? So this is the mechanism by which we are going to shape behavior. Okay, so what are the advantages? Well, we don't actually require the opponent's policy parameters. We do require an estimate of the opponent's value function, but that's actually a lot easier, right? Because we don't actually need the correct parameterization. We can actually learn that. Right? We're not dependent upon the gradient updates there either. So I think it's a much less restrictive assumption than what we have in Lola. But we can, again, discuss how important that kind of assumption is. The second point here is that the gradients of the reinforced estimate that we're heavily relying on are unbiased. They are, though, relatively high variance. So that's something we should think about for future work. And finally, yeah, it's fast. These estimators are fast to compute. We are not building this giant giant computational graph that we have to backprop through. So that's the whole thing that we're trying to get, is something that works and is effective and relatively quick. So we've applied LOCA to IPD, and what it learns is roughly a tit for tat strategy. So what does this look like? So the first bar there is the initial policy, which sides towards cooperation. So that's like tit for tat. What does it do? First move, it cooperates. And that's what we're seeing here most of the time. CC, this is what happened on the previous move. So if both agents cooperated on the previous move, we have probability roughly probability one that the agent will cooperate on this move. CD, which is the agent, our agent cooperated, but the opponent defected. So that's the case where you want to punish the opponent, right? That's the tit for tat strategy. And you can see the probability of cooperating goes down to like 0.2. In DC, so when you've defected in the last turn, but the opponent cooperated, you're going to then cooperate again. And of course, when there's a defect, so both players defect in the previous turn, you're going to defect as well. So this basically carves out kind of a soft version of tit for tat. So it's able to recover those kinds of dynamics. If we apply this to the 3x3 coin game, what we're actually showing you here is how it plays against other kinds of agents. So we compare LOCA, which is the top corner there, against POLA, against another method called model-free opponent shaping, which is another method that was out. There's actually quite a bit of excitement in that group around MFOS, but our experience is that POLA is actually a much stronger algorithm, at least what we found up till now. Yeah, thanks. And then we have always cooperate, always defect, and finally against a random player. What you can see is that, so again, our big competitor here is POLA. And what you can see, I think, is that LOCA, when it plays against itself, actually does very well compared to POLA. When POLA plays against itself, POLA actually ends up learning a strategy that is more exploitative. And so when POLA plays against LOCA, POLA actually does better. It's more able to exploit LOLA, but at the same time, when it plays against itself, it's also exploitative. So it actually doesn't do as well against itself. So I think there's a lot of interesting questions to ask. How do you take a table like this and resolve like what is the better strategy? I think there's a lot of discussion. It's not at all obvious to me how to come up with a single number that tells you how good a particular agent is, but this is what we found. Now I'm going to skip over the movies in the interest of time here, but there's nothing really that insightful about it. It's basically that LOCA learns to basically cooperate against an always cooperate agent. LOCA learns to basically defect against an always defect. Not initially. Initially, it starts cooperating, and then it learns its lesson, and then starts to defect all the time. LOCA versus LOCA mostly cooperates. So we were interested in developing a method that was scalable, and so that's kind of what we're going to show here. So we're comparing different kinds of agents, specifically a POLA agent and a LOCA agent. So LOCA is our method, and POLA is what we consider to be the previous state of the art. And we're looking at normalized return against themselves. That is to say, a LOCA agent against a LOCA agent, and a POLA agent against a POLA agent, and normalized returns against always defect. And so we're looking at sort of a weak, medium, and strong category of agents here. So just relative performance against these other kinds of agents. And this is the kind of plot we're seeing. So, and we're measuring across wall clock time, and this is for different sizes of the coin game here, right? So what I was showing you up till now was for a 3x3 grid size. We're going to 7x7. These are not massive games, but you can see that we're stress testing POLA, both methods here really. But you can see that the scaling on POLA, on POLA is much worse than for LOCA. We're getting much better performance from a wall clock compute time point of view, which is exactly what we were aiming for. And we even see that for the strong threshold, that is to say, a relatively strong agent, that we're actually not able to get very strong performance out of POLA past the 3x3 grid. So just to give you a sense of what that looks like in terms of the learning curves, this is POLA versus LOCA in a self-play scenario versus an always defect agent. And you can see that, POLA is generally, you can also just note that the wall clock time here is at a different magnitude between the two. But you can see that POLA doesn't achieve the same kind of performance, but it's much less high variance than our LOCA agent. Our LOCA agent, this is 3 random seeds. So this is 3 attempts at training. And you can see there's quite a bit of variance there. And it makes sense, we're heavily relying on this reinforced estimator, which is a high variance estimator. So yeah, there's work to be done in terms of improving that, but I think we're on a very interesting track with this kind of work, at least in this direction. All right, and with that, I think I'll stop. Thanks very much for your time. And just a limitation, future work, we're actually interested in extending this towards continuous spaces. A limitation is that right now it only works with discrete actions, and it only works if the agent's policy roughly follows this Q function softmax that we've been doing. We make this approximation of. As long as the agent is rational in following kind of what it determines to be good behavior, that doesn't seem to be too much of a restriction from my point of view, but it is nonetheless a potential source of failure for this method. All right, thanks.
Hello, I have a question.
Oh, that's nice.
Hello, Professor, I have a question.
Yeah.
So actually you mentioned the agent can, in your first scenario, the agent can cooperate and, in the worst scenario, the agent want to, cooperate, but the other agent do not want to, cooperate with each other. So in that situation, so that is the real case. But in the simulation, we just force the agent maybe cooperate and cooperate and do not cooperate. But in the real case, agent receive the the environment feedback. They will analyze based on their, like you said, the inner value system to whether or not this kind of behavior can benefit the agent current situation. They will select which kind of the agent they want to cooperate, and which whether or not they do not cooperate with other agent. So in that case, whether or not we can develop another kind of model to model those kind of agents, the behavior to let the compare with the traditional reinforcement learning mechanism, let them to more fit for the humans the perspective. Yeah.
Okay, so there's let me see if there's two things in that I think I want to address. The first thing is whether or not we want to consider the case where we're training an agent in what I would call a training harness and then deploying a fixed agent, which is, by the way, like almost all what we do in machine learning is that scenario, right? We're never, well, almost never, unless it goes disastrously wrong, like there's been cases of that. But we generally speaking never deploy agents that are actually learning. So that's the way in which I say that Lola and Loca by extension, I don't consider it to be much of a problem that we're giving them special dispensation during training to know about their opponent. It's a training harness. It means that you can't train these agents in a deployed online scenario. And by I mean online, I mean truly like out into the world and interacting with the world. They cannot train under those assumptions in that scenario. But I would say most of the time you don't want that anyway. What we want are agents that are able to behave in a cooperative way, but yet still remain unexploitable. And that gets to your second point, which is I'm not doing anything like changing the game for these agents in the sense that I am not saying that you must cooperate. I'm not giving them a reward explicitly for cooperating. And that's important. These agents are playing their original game. They're just learning that through the interaction with the other agent in a self-play scenario, if they do something bad like defecting, you'll pay for it. The agents are learning to reciprocate bad, sort of antisocial, if you like, behavior. And so they are learning that themselves. So they learn it is rational for me not to do that because I know what's coming. And we're just providing a mechanism where you can kind of see that behavior manifest. Whereas in an pure RL scenario, there's something about the game dynamics such that they can both just sort of, because they're never assuming the other agent's really going to respond to their policy. So they both just slide towards defect. It's like a coordination problem, but in the training dynamics itself. I don't know if that helps, but I think that's my answer. Yeah.
Okay. Thank you.
Okay, so that was a cool talk. I like it. I definitely like the idea of trying to figure out better ways of updating in coordinated settings. The question I have is related to exactly like when would this work well, and what would this actually converge to, right? Because you're certainly changing the value space, but you have no idea like what that's gonna actually
Right.
cause.
Yeah.
And so it seems like you're gonna convert to some other possibly Nash equilibria, but really it's a circular problem. The agents depend on each other. So the only way to really solve it is you'd have to solve the full game and find the Pareto dominant Nash equilibria. And
Yeah,
so
well, the issue with concepts like Nash equilibria or any other kind of equilibria is that they don't generally, there's lots of them there. Like always defect is a Nash equilibria for IPD, right? It's just, there are some that we decide we like better than others, right? And so we're interested in, so yeah, I mean, I think we're struggling a little bit to find correct solution concepts that are helpful for what we're looking for here. But that's why from a certain point of view, RL is actually kind of an appropriate tool, because at the end of the day, we can see when we play against other agents, our return is higher if we actually do this kind of social dynamics. So if we're just worried about what equilibrium or just getting into an equilibrium, like there are differences between these equilibria, right? And so yeah, that's kind of where we're at. And in terms of characterizing it, yeah, we don't have a great characterization right now for these. I'm hoping that comes. It's complicated, right? As I'm sure you know. But I guess I feel like we're in a situation right now where we have pretty advanced agents that are now being used as products in the world, and we are at the threshold of them being deployed as genuine agents into the world, where they're going to be interacting with people and interacting with themselves. So I don't think we can wait for the theory to advance to the point where we're actually seeing these things, where we're actually carefully characterize these from a theoretical point of view. We need to deploy agents that are capable of getting out of sort of these negative interactions. Yeah.
yeah, thanks.
Thanks.
All right, thank you.
Thanks.
All right, and now we have a series of contributed talks. Hopefully the first contributed talk speaker is here. Yay, awesome. So I believe they're going to switch over. I'm just going to delay. Your name isn't on the schedule.
Oh, it's not.
No. Okay. So I'd like to introduce Min-Woo Lee from
Seoul National University.
Seoul National University. That's a long trip.
Yes, but my home is actually in Canada, so I've actually come from Langley.
Awesome. Welcome home.
Yeah, for now.
Still delaying while we're waiting for the slides.
I see. So I found that the presentation, the 10-minute presentation is actually quite short to discuss. But there are lots of discussions to be made on the results side, on the results and the experiments I've conducted, and I can't mention all of those as well as the preliminaries. So I'll try my best to outline the key ideas, and then hopefully we can discuss more later through the Q&A session or the poster.
Awesome. And just as a reminder, if you have a poster today, you're welcome to put it up and we can talk about it anytime outside. There'll definitely be time over lunch. Oh. Okay, didn't have to go into dad jokes.
Okay, I see.
You know where you store your dad jokes? Where? In a database.
Mike,
Slide advance.
is it this? Okay, this seems to be working. The laser pointer is also working. Nice. Okay, so as I've introduced myself, I am Min-Woo Lee. I'm a PhD student in Seoul National University. So my focus was on applying multi-agent reinforcement learning on out-of-distribution, adapting to out-of-distribution settings. So, oh, wait, it's this one. Where should I point to when I want to? Okay, So here's a brief outline, but I'll just skip over this and then move on directly to motivation. So the main motivation is that if we want to apply the cooperative MARL algorithms to the real world, we would first need to address a few challenges. One of the challenge, of course, is that the real world is often only partially observable. The agent can only observe its own surroundings. And then in order to gain the understanding of other agents, they would actually need to cooperate by some method. And another challenge is that if you want to apply the trained agents in the real world, there is bound to be some discrepancy between the training and the actual test setting. So those have to be addressed as well. Of course, it's multi-agent system. So the unique feature of multi-agent system is that we can use communication to share information that can be helpful for the task, helpful for actually telling what's going on around them, as well as telling what's unexpected around them. And I would like to mention a brief assumption about the communication here, that the agent can choose a communication action, communication symbol, in the time step t, and then it gets shared all across to the other agents, broadcasted all the way to in the next time step. So there's a 1 time step delay in my setting. So I'm not sure if that was much of a motivation, but so the main goal is to address the out of distribution setting and how to, and then the method I was focusing on was the communication. So we proposed the communication architecture called the unexpectedness encoding scheme with reward, which we shortened to UESR. And as suggested by the plus sign over there are actually two components for the message. The first part, the unexpectedness encoding, is the main contribution. So what this does is that intuitively we want to, if the agents encounter an unexpected surrounding, they would need to communicate what aspect and how unexpected it would be. So in order to do this, we first came up with the anticipation by using the 4 dynamics model F, which is in the red box over there. It uses the input from the time step t-1 to yield the prediction for the time step t. So it's done in hindsight, and that predicted observation is compared with the actual observation that we obtained at the time step t. This we formulate as unexpectedness, and we keep it as a vector rather than a scalar, in order to actually retain the information of what aspects of the observation is different from anticipation. And then we simply encode this using the autoencoder to form the first component of the message, which we call the unexpectedness encoding. This would be the MTI over here. This would be the MUSTI over here, and it's labeled as MTI over here, so that's a slight mismatch in the notation. But anyway, and these are simply trained by using we have 2 different components to train. So one component is the autoencoder over here, and another is the 4 dynamics model over here. These are simply trained using the reconstruction loss for the former, and the observation prediction loss for the latter. Oh, right. So that was the first component of the message. And the second component actually comes from the extrinsic reward. So this idea is simple. We also use the extrinsic reward simply because the unexpectedness encoding only tells what part is unexpected, and it may not necessarily tell what part of this unexpected surrounding is actually relevant to solving the task. So we included this information by simply implementing a message policy pi_m, and we trained this using the same loss function that is used to train the action policy pi_a. So this would come from the objective function from the algorithm of the choice, such as SAC, PPO. I used A2C here actually, so that's where it comes from. So the two message components are concatenated to yield the final message, MTI, and that would be our proposed method. And here we conducted some experiments. So one thing to note here is that I actually conducted on the training. So there was a training distribution of, skipping ahead, there actually is a training distribution of environment that has been designed. And and after training on this training distribution, the transfer learning performance on the out of distribution setting has been tested. But moving back, we have a few baselines. So the IA to C over here is the independent A to C, which does not communicate. IA to C MR and MUES are ablative methods that only use the reward-driven message or only uses the unexpectedness encoding. And combining them would yield our method. And the MAPPO here is simply put here just for mainly for how well it can do as an upper bound. The environment we used is the multi-robot warehouse, which is created by Giorgio. I'm not sure how to pronounce it. Giorgio Papadakis, I think. And the goal is to the orange circle over there is the agent. The agent have to move around in the grid world and pick up and deliver the red shelves all the way to the green green tile on the right, which would be the goal location. And actually, I haven't described it over here, but they actually have to put back the shelf and then pick up the other requested shelf, which would be in the red. The training distribution is actually made to be dynamically changed by randomizing the position of the impassable obstacles in the black every 1,000 time steps, which would be like 10 episodes. And the out of distribution setting is that first we conducted the training for 10 million time steps, and then we transferred them to the settings that have never been seen during the training. So we note here that so there are two different settings over here: goal shift and the shelf shift. Goal shift is the setting where there are actually additional goal positions. They can be exploited to make the task easier. Shelf shift is, on the other hand, makes the task somewhat harder by moving the shelves to the wall and making it harder to pick up the shelves that are closer to the wall. And the metric we used here is the average number of delivered shelves per episode. And here are a brief results. Okay, so it is interesting here to see that when we use the reward-driven message or the unexpectedness encoding individually, it actually did not do much better, or it actually did not do much better than actually not communicating at all. However, when we combined both of them together, they actually showed the complementarity and almost achieved the performance that is close to centralized training method, MAPPO. The similar trend has been seen in the out of distribution setting. So the previous slide was the training setting. In the out of distribution setting as well, our USR actually does better than the other ablative methods. However, it's also interesting to see that MAPPO has overfit to the training setting and does not do much better than the independent A2C. So what we speculate here is that it is actually important to actually selectively emphasize which part of the environment is unexpected and actually which part of this unexpected environment is actually relevant to task solving. Both of these are needed, we think, in order to robustly generalize to some unseen settings. So those were the main takeaway points. I would like to finish the talk very quickly by mentioning just a few paths for future works. So we still yet have to find out what kind of information these messages actually contain. So interpreting them, there are multiple methods for interpreting them. I think we would have to use them to figure out what kind of information is stored in them. And the task we used here is actually, they don't necessarily require a precise coordination of agents working together at the same time to deliver delivery shelves the goal. So we would want to test this on more cooperative setting cooperative setting that requires coordination as well. And that would be the end of my presentation. If you have any questions or comments, please feel free to ask now or during the poster session. Thank you.
Thank you for a great presentation. I'm coming from a causality background, so slightly different, but certainly related. As I understood your talk, the agents are communicating about the surprise, about the environment itself.
Yes.
But we can imagine a situation where there are some factors within the environment that are not observed by the agents for whatever reason.
Right.
And those factors could surprise the agents, not in terms of the setup of the environment itself, but rather regarding the mapping from the observed environment to the reward.
Mm.
Is that something that you also took into account in this work? And in general, what are your thoughts about such a setup?
Oh, I couldn't actually hear the second part of the question.
So the second part of the question was regarding your thoughts about a setup like this.
I see. So in our setup, we didn't actually take into account the surprising elements that could not be observed. But if we were to deploy the agent in the actual setting, in order to actually know about the unexpected setting that would not be observed by the agent yet, I think we would need some sort of central agent that actually knows what's going on outside the individual agents. The setup I adopted here was mainly decentralized, mainly because I thought it would be we thought it would be too expensive to actually conduct some sort of centralized training in the real world. There would be some communication. There's be some communication bandwidth issue and the cost issue. So yes, so the agents here rely solely on the observations. So that's the setup we adopted.
That's clear. So maybe a follow-up question, or maybe a little bit of clarification. So I imagine that we can have a situation where the environment is the same as previously seen, but the mapping from this environment to reward is different. And there is some unobserved factor that is actually impacting the mapping from the observed environment to the reward.
Ah, I see. So I think that would, so the case where that could be the issue would be when the environment is highly stochastic. So in the case where the agent has, in the case where the environment is not stochastic and the agent has sufficiently explored the surroundings, I think the unexpected part of the original training environment wouldn't be much of a problem, I think. But in the case where the environment is highly stochastic and randomistic, it would cause a problem. We didn't take that into account yet, and the environment here is quite deterministic. I think we would need some form of uncertainty modeling in order to communicate and in order to quantify which part of the unexpectedness comes from the unknown part of the stochasticity of the environment and which part comes from the change in the environment. So some form of future work could be done in that regard.
Thank you.
Thank you for the comment.
You again. Video from a participant who is visa, or rather, I guess they were not visa. They should be in a Zoom meeting though, so if we have a question after their video presentation, hopefully they'll be able to respond. So start thinking of one really hard question.
Hello, everybody. My name is Qing Yang. I'm assistant professor in Brandling University. Today, I will represent my paper, Bayes the Soft Act Critic, a direct Hello, everybody.
Hi, everyone. My name is Devansh Jaloda, and today I'll be presenting our work. Hi, everyone. My name is Devansh Jaloda, and today I'll be presenting our work on balancing efficiency and fairness in traffic routing via interpolated traffic assignment. So to just start off by motivating our work, I'll start by just giving a very simple example, that of routing 5 units of users between San Jose and San Francisco. So out here, I'll denote X1 to be the flow on the green route, X2 is the flow on the red route, where the total flow must add up to 5. And also I'll denote the travel time on the green route to be a function of its flow given by 2x1 square, and the travel time on the red route to just be a fixed constant of 50. Now, in this particular context, if we do not impose any regulations or any form of tolls in the system, then users will just selfishly minimize their individual travel times. And this will result in a traffic outcome where all the 5 users will end up using the green route. And this is a so-called user equilibrium, wherein no user can benefit by deviating to another possible path, which in this case is the red path in the system, and potentially improve their travel times. However, if we look at this outcome closely, clearly all 5 users traveling on the green route can lead to a potentially bad outcome in terms of the overall level of traffic in the system, wherein the total travel time in the system, which I will denote as FSO of X, is given by 250, which is because all the 5 users now incur a travel time of 50, giving us a total travel time, which can be a potentially large amount of 250 within the system. Now, clearly, what you can note is that if we just distributed these users in a better way across these 2 routes, we could have achieved a better outcome in terms of the total travel time within the system. And in fact, the lever that we can use to achieve this better distribution of users across the different routes is by using some form of tolling on the different roads, for instance, marginal cost tolling, that can help steer the traffic from this user equilibrium outcome that can have potentially long travel times to one that is a system optimum, wherein the total travel time of all users is minimized. For instance, we could have set tolls appropriately such that only 3 users use the green route while the remaining 2 use the red route. And the outcome of this would be that now our total travel time is reduced from the original amount of 250 to just being about 154. However, if we look at this particular outcome as well quite closely, what we observe now is that while some users incur much lower travel times of just 18, there are other users, these 2 red users, which incur a travel time of 50, which is almost 3 times the travel time of that of the users on the green route. And so in some sense, this particular outcome can be perceived as being unfair, as some group of users are being made to bear the burden of the longer travel times, which typically are the lower income strata within society. So essentially, if we now just summarize this stylistic example, it reveals a very clear efficiency fairness trade-off when we compare these 2 different solutions, wherein the user equilibrium outcome is fair by definition, as all users between the same origin and same destination incur the same travel times. However, it is potentially inefficient, as we saw in this example, as the total travel time in the system can be quite high. On the other hand, the system optimum solution is designed to be efficient, as it minimizes the total travel time in the system, but can potentially be quite unfair, as some users may bear the burden of much longer travel times than others, even though they're traveling between the same origin and destination. Right? So what we observe is a clear efficiency fairness trade-off between these 2 contrasting outcomes. And so essentially, the main goal of this work is try to somehow achieve a good balance or be able to resolve this trade-off. And the way we do this is through a 2-step procedure. First, we develop an efficiently computable traffic routing algorithm that tries to balance these objectives of efficiency and fairness. And secondly, we combine that with a road tolling scheme to in fact implement this, the the traffic routing policy that we recommend through our algorithm as flows that we can actually induce in a system as an equilibrium outcome in practice. And the final outcome is that we're able to actually balance efficiency and fairness in traffic routing in a way that's both efficiently computable and implementable. So the way we're going to evaluate the performance of any routing policy within a network is by two metrics. So the first metric we're going to use is that of efficiency. And in particular, to evaluate efficiency, I'm going to, for any given vector of edge flows X that is computed by our routing policy, I'm going to compute a quantity called the inefficiency ratio, which is essentially just the ratio of the total travel time of our particular vector of edge flows given our routing policy X, and divided by the system optimum travel time, which is the minimum travel time possible in the system. And note here that the inefficiency ratio is always going to be at least 1, as the denominator is the best possible within the system. On the other hand, we're also going to look at the metric of fairness. And the way we define fairness in this work is going to be by defining a metric called the called the unfairness, which takes in a vector of path flows and computes the maximum across all origin destination pairs of the ratio of travel times of users traveling between that particular origin destination pair, right? And essentially what we're going to try to do in this work is somehow balance these objectives of efficiency and fairness. Now, to be able to try to balance these different outcomes, I'm going to define a problem called the beta unfair system optimum, wherein the goal is essentially to maximize efficiency or minimize the total level of travel time in the system, subject to an unfairness constraint, which essentially just states that the total level of unfairness in our system must be no more than some parameter beta, which you can think of as being specified by, say, a municipal authority. Okay, and this essentially guarantees that all users in our system are equally treated up to some factor beta. However, now if we look at this problem a little more closely, we have essentially a non-convex optimization problem, which is generally going to be quite computationally intractable. So essentially what we're going to need to develop is a good approximation to this global optimization that achieves still a good outcome in terms of the level of efficiency while satisfying our fairness constraint. So in order to motivate our algorithmic approach, I'm going to just out here introduce two classical traffic assignment problems. The first one is that of the system optimum traffic assignment, which essentially minimizes the total level of travel time within the system, which is just looking at minimizing the total travel time without these unfairness constraints that I mentioned on the previous slide. And it, in this particular context, note that out here, our level of inefficiency in the system is 1, that is, we have the best possible efficiency within our system, while our unfairness can potentially be larger than 1, as we saw in the example earlier. That is, the system optimum traffic assignment is efficient, but potentially unfair. On the other hand, the second traffic assignment problem is that of the user equilibrium traffic assignment, wherein all users between the given OD pair incur exactly the same travel time as an outcome of the solution of this traffic assignment. And in particular, the user equilibrium can be computed by the solution of the following convex program. Here, the inefficiency ratio can be potentially larger than 1, as we saw in the earlier example, but our unfairness is guaranteed to be exactly equal to 1, right? And essentially, our algorithmic approach is going to leverage the fact that the user equilibrium is fair, but the system optimum objective is efficient. And in particular, what we're going to define is a so-called interpolated traffic assignment problem that interpolates or takes a convex combination between the system optimum and user equilibrium objectives, such that we can somehow get the best of both worlds of the user equilibrium and the system optimum outcomes. Okay, so just to go back to our original problem, as I've introduced this ITAP, or the interpolated traffic assignment, is that what we really wanted to solve was this beta unfair system optimum problem that we started out with. However, solving this problem, as I mentioned earlier, is quite computationally complex as we have a non-convex problem. So what we did was we developed some approximation for it through an interpolated traffic assignment problem, where we're just minimizing a convex combination of the user equilibrium and system optimum objectives, which is a far more tractable problem to solve, as now we have reduced and removed these unfairness constraints, and what we have gotten is just a convex program that we're solving at the end of the day. Okay. Now, the next question is how good an approximation really is our ITAP approach compared to the original problem that we wanted to solve of the beta unfair system optimum. So to do this, what we first do is we develop some theoretical bounds to evaluate the efficacy of ITAP. So in particular, we have some upper bounds on the level of inefficiency that we have as we vary this convex combination parameter alpha within our system. And secondly, what we also have, so essentially what this upper bound states is that for any given convex combination parameter alpha, what is the maximum level of inefficiency that we can achieve within our system. And this is plotted for a particular traffic network, but we have the more general bound at the bottom of the slide. Secondly, what we've also obtained is some upper bounds on the performance of the unfairness. That is essentially to state that for any given unfairness level that we so desire, let's say 3 is the level of unfairness that we want to guarantee within our system, then if we choose a convex combination parameter of at most 0.5 in this particular context, then we can guarantee that we will certainly achieve an unfairness of no more than 3. So essentially what we have here are bounds on both the level of efficiency and fairness within our system that we can guarantee. Okay. And what I want to mention here is that we also did some numerical experiments which compared our algorithm in blue to that of a state-of-the-art given in red. And essentially what we've plotted here is our Pareto frontiers of the inefficiency and level of unfairness. And the broad takeaway from this work is that for low levels of unfairness, our approach achieves lower travel times than the state-of-the-art. And in general, our approach, especially for these particular traffic networks, for pretty much all levels of unfairness that we might desire, our approach achieves low total travel times than the state-of-the-art algorithm. Okay, finally, what I just want to quickly just wrap up by mentioning is that it's not just that we have a method to route users within the system using our ITAP approach in a very computationally tractable way, but in fact, we can also get a pricing mechanism just by design that helps actually implement our outcomes in practice. So in particular, our ITAP problem can be rewritten as just a special case of the user equilibrium problem with just a slightly different objective with this additional term that we have here. And this essentially leads to a type of tolling that we call interpolated marginal cost tolls, which is multiplied by a factor of alpha, depending on our convex combination parameter that we choose. And this, in fact, if these are the tolls that we set in the system, this will indeed influence and induce the overall level of traffic that we desire as computed by our ITAP method. And this happens with homogeneous users when this method applies with homogeneous users when all users have the same value of time, but we can also develop some linear programming approaches that can help generalize our procedures even in the setting with heterogeneous users. Okay, so just to finally wrap up, what we developed in this work was an efficiently computable traffic routing algorithm combined with a road tolling scheme, both of which combine to help balance the efficiency and fairness objectives in traffic routing. And here's the link to my email as well as an archive link to the paper. And I hope you enjoyed the talk. Hi, everyone. My name is Devansh Jaloda, and today I'll be presenting our work on
safely move on to the third talk, which is also a video. And after this, we'll have a lunch.
Hello, everybody. My name is Qing Yang. I'm assistant professor in Brandon University. Today, I will represent my paper, Bayes' Soft Act Critic, a direct, circling strategy graph-based deep reinforcement learning. And I will separate the 4 parts to introduce this paper. First, let us have some background knowledge about this research. In artificial intelligence, a strategy describes the general plan of an AI agent achieving short-term or long-term goal under conditions of uncertainty, which involves setting sub-goal and priority, determining action sequence to fulfilling the task, and mobilizing resources to execute the actions. In reinforcement learning, a strategy is the rule used by agents to select an action to pursue goals, which is equivalent to a policy in a Markov decision process. The policy indicates the action that the agent takes as a function of its state and the environment, and the goal of the agent is to learn the policy, maximizing expert accumulative the reward in the process. With advancement in deep neural network implementations, deep reinforcement learning helps AI agents master more complex strategy and represents a step toward building autonomous systems with a high-level understanding of the virtual world. Especially the deep reinforcement learning is ideal for robot manipulation and locomotion because there is no predefined training data requirement. Furthermore, the control policy could be obtained by learning and updating instead of the hard-coding directions to coordinate all the joints. There still have some challenge in deep reinforcement learning currently. In most cases, complex strategy and system usually consist of the multiple tackles or subsystems governed by corresponding sub-policy, which represents a joint policy in real-time interactions. Second, a single strategy might involve learning several policies simultaneously, which means the strategy consists of several attacks and actions executing a task, especially in robot locomotion and real-time strategy game domain. Last, although achieving some progress, deep reinforcement learning still hard to explain formally how and why randomization works, which brings the difficulty of the design efficient model expressing the relationships between various strategies. The second part, we will briefly discuss our approach. First, let us have some preliminary knowledge about our approach. The first is the Bayes network. A Bayes network is the probability graph model for representing knowledge about an uncertain domain, where each node corresponding to a random variable and each edge represents the conditional probability for corresponding random values. Second is the soft act critic. SAC is an off-policy act critic algorithm that can be derived from maximized entropy variance of the policy iteration method. It used an entropy regularization in its objective function, which trains the policy to maximize a trade-off between entropy and expert return. So for our method, we introduced incorporation of the Bayes networks to decompose a complex actor into several simple sub-actors or sub-policy termed as a Bayes strategy network. So the red picture, I just give you guys an example of the robot dog model using BSM. Then we integrate the idea of the maximized entropy reinforcement learning framework in SAC, design the method that result in our Bayes soft act critic approach. And the red picture is an example of the proposed BSN-based implementation of the act critic DRL architecture model. So for our model, the objective functions for each sub-policy evaluation step of the solved policy iteration. The joint policy phi will calculate the value to maximize the sum of the subsystems pi's entropy in BSN using the below objective function. And consider that the evaluation of each sub-policy applying the same Q value and weight. The solved state value function can be represented as below. And the joint policy parameters can be updated by minimizing the expert KL diversions. Last, the loss functions. The solved value function is trained to minimize the square resident value of each sub-policy in BSN. We define the loss to be the expert value of the mean square TD error caused the sub-policy as below. Next, for the evaluation, we choose the OpenAI Gym Juco as the experiment test bed. And we compare the performance of the proposed BSAC agent to prior technology on a range of the challenge continuous control tasks from the OpenAI Gym benchmark suite, like the Hop, Work2D, Ant, and Humanoid. And this is our experiment result. The quantitative result attained by the BSAC in our experiment indicate that both the sample efficiency and the stability of the BSAC on these benchmark tasks exist the state of the art. We also conduct an ablation study on one typical Majorco environment, Ant V4, which is adequate to show the influence of different parts and parameter of the BSAC. Last, I will give the conclusion for our research. So for this research, we introduced a novel agent strategy decomposition approach termed based strategy net to achieving efficient deep reinforcement learning. Based on the SAC algorithm, we propose a new DRL model termed as the Bayes soft act critic, which integrates the BSN and form as a joint policy better adapting the Q value distributions. So for the future research, I list the three directions. First, for the multi-agent system, we want to implement our approach in the multi-robot system and the self-driving car. And for the real-time strategy game, we want to implement in the StarCraft 2 and OpenAI video game environment. And for the robot locomotion, we want to implement in the Unitary Go 2 and local board WX250s. So this is my presentation. Thank you much.
Hello, thank you for your. Is my voice coming through? Thank you for your talk. This might not be on exactly the same relevant question, but I was wondering. So we can consider every joint or every arm leg of a robot as individual agents, and I was just wondering how far we can or how far we would often want to decompose like into a single agent. How much we would want to allocate to a single agent.
Hello,
Have any?
is this a question?
Yes. Do you have any opinion on on that?
Okay, can you repeat again? Sorry, I did not heard pretty much.
Oh yes. So in short, I was wondering how much we would want to break down a single complex agent into into a group of agents. So every arm can be an agent, every finger joint can be an agent. Maybe some level of the composition is too excessive. Maybe some are not enough. How do you have an opinion of how we would want to decide on that?
Yeah. That is actually pretty good questions. Actually, when you presented is the robot arm. Actually, robot arm, each arm can be treated as an individual agent. But actually, how to organize those individual agents to cooperate with each other, so to form the specific gesture to, for example, pick up the item or represent different kind of the position. So it's a really what for in just like our paper, it's really depending on how to design the specific reward mechanism. The other is how to build the specific model based on the relationship between each agent. So that is the two key point to design this mechanism to implement in the real world, especially the multi-agent system. Is that answer your questions?
I think so, yes.
Okay,
Thank
thank you. Yeah.
Thank you, Chen.
Yeah, thank you.
And next up, learning communication policies. 4, different follower behaviors in a collaborative reference game.
Thank you. All right. So is this presenter view? No, but okay. So I improvise. I have my notes on the slides, but okay. Yeah, my name is Philipp Sadler. I'm a PhD student at the Computational Linguistics Lab in Potsdam, Germany. So, and as computational linguist, I want to present this work towards more interactive language generation or language agents. And let's see if this works. Yeah, all right. So why learning communication policies? So I just wanted to motivate with a quick example using an arbitrary large language model that has been chat optimized. What should I bring home to Germany when visiting Vancouver? And I get this nice list of 10 bullet points. Well, it was quite quickly generated, but you can imagine if I read this out loud, it takes me this talk. So how humans actually communicate, it's more like this. We have this incremental process in the conversation where we add one information at a time. Like here, for example, a word at a time when visiting Vancouver. And so every time the agent produces a word, it gives back control basically to the environment, which is here in our case myself. So I could intervene or add some information as well, or the agent could decide to maybe stop the production. So this is why we find that the reinforcement learning setting is a nice framework to model such interactive learning, where we have a communication policy here, like the chatbot, and the environment, the user, which receives the word at a time, and the policy can observe the user's reaction, actually do something else, for example. So it's more like we have some control over the language production, while there's like an underlying language model or something. So having this set up, I want to motivate more why different follower behaviors. And here we are interested in a quite old line of work from Herbert Clark and Wilkes Gibbs, which is from 1986, referring as a collaborative process. And they have this interesting task where they let two people, a director and a matcher, arrange these tangram figures. And only the director knew the correct order of the figures to be placed, and the matcher has to somehow they had to coordinate so that the matcher could do the same order on his board. Now what they observed is two things. They had 6 trials to perform this task. In the first trial, it was like the director said something like, all right, the next one looks like a person who's ice skating, except they're sticking 2 hours out in front, and so on. And later, they say the following things. So, and one thing is to see that they agree on newly introduced terms. So the person who's ice skating becomes an ice skater later. And secondly, we see that the speaker is using less and less words after each trial because they kind of adapt to each other. They found something they can agree on. And quantitatively, they had this figure. So the mean number of turns by the director per figure, per ice skater, for example, decreased over the number of trials rapidly, meaning that the speaker put less effort, or, well, meaningly, they agreed to minimize a joint effort, and the speaker on his side minimized his effort, producing less words, for example. Now, we assume that this has something to do with the confidence of the other one executing the actions. For example, like the ice skater now, and later trials means the matcher knows what to do. And here comes in the idea of different follower behaviors, where in the beginning, the confidence C of performing an actual action in the environment is lower than in later turns. But for means of experimenting with this, we leave these fixed, basically. So we experiment with a fixed follower that has confidence of 75 and so on. And we assume that the speaker, in our case, so the director to say, produces more silence actions when interacting with more confident follower behaviors. All right. And since we have not enough interaction data available, or we cannot produce a lab with thousands of participants and record all of these interactions, we come up with a collaborative reference game where notably the guide produces a sentence like takes a blue X, and the follower is using this information and has to navigate to the blue X here, which is basically kind of a navigation problem. And notably, the guide, the follower has this confidence of executing the actual action or is performing a waiting action from the plan. And the guide can also choose the silence action. So what is not on the slide is that we assume an effort of producing these different intents from the guide, like silence is the least effort for them. So it will later give a higher sparse reward, while, for example, producing the takes a blue X is requiring a higher cognitive load, and so it will give a lower sparse reward in the end of the episode. And also the reward is so that it's only positive when the actual piece is taken in the end of the interaction. All right, so that we have everything in place, we measured the experiment and produced several runs with recurrent PPO and 3 random seeds for each pairing. And indeed, we could see, at least for the more confident followers, that the speaker is increasingly producing more silence actions instead of producing like as a reference action or confirmation action. Like it seems to be able to, or it's promising finding that the speaker in a multi-trial setting would be able to adapt if the other agent is increasingly confident about doing its actions. So this is why we could not see this effect with the low confidence. So there's a high variation, the production of the silence actions for the speaker. Right. Whoops. Okay. So there's some delay. So yeah, this is our main finding. So I wanted to just take the time actually, and maybe I had more on the notes, but to motivate more our approach. And if you have questions, you can gladly ask them at the poster or have a look at the paper.
You're always welcome to ask questions at the poster later. And then last up in this section, we've got a final video.
Hello everyone, I am Zhilei Fan from University of Science and Technology of China. Today, I'd like to introduce our work about training framework for multi-agent imperfect information games and demonstrate our method performance using margin and bridge training tasks. Here, my presentation is divided into 4 parts: background, method, experiment, and summary. First, I will introduce the background of multi-agent imperfect information games AI training tasks. Multi-agent imperfect information games serve as an abstraction of real-world problems, offering a cost-effective platform for benchmarking artificial intelligence algorithms. The dynamic and complex nature of these games presents unique challenges in the realm of AI. Historically, game AI methods like heuristic algorithm, decision tree, and supervised learning are heavily dependent on extensive expert knowledge. These traditional approaches, while effective to a degree, are limited by their reliance on predefined rules and human-derived strategies. Deep reinforcement learning has made AI can achieve impressive results without expert input, even outperforming humans in some scenarios. However, multi-agent environments, especially those with imperfect information, demand a significantly large scale of data for training, posing a challenge for existing methods. Current distributed training algorithms and frameworks, though efficient in complex environments, are not specifically tailored for multi-agent games training. In this work, we focus on AI training framework for multi-agent imperfect information games and take margin and bridge for example. Multi-agent imperfect information game is usually described as a partially observable markup decision process and is defined by a tuple composed of N, S, O, A, P, R, gamma. The physical meaning of each item as below. Now, let me introduce our method. We propose a distributed reinforcement learning training framework. We deploy the self-play methodology. The distributed RL training framework consists of actor module, learner module, and allo module. The actor module generates data in parallel, sends data to learner module. The learner module autonomously for training the model and receives the latest weight file to form a training loop. The allo module obtains the latest model as regular and performs game evaluation with the agents of the opponent list. We use two tricks to enhance the efficiency of data generation in games AI training. First, we use container isolation method. The actor module is comprised of 160 parallel interactive processes, each process hosting 4 agents that dynamically interact with the game core. Docker is employed to segregate processes in actor module, learner module, and allo module. Consequently, 160 Docker containers are isolated, and each process is executing independently. Secondly, we use address mapping in the deployment of the training framework. We map the addresses of all containers in actor, learner, and allo module to a same physical address on the server. This method makes each process of fetch data and file directly, without network transmission delay. These direct access methodologies effectively alleviate the burden on network transmission. Here are the training details. We use self-play PPO algorithm for training. We use PPO clip as policy loss, and use GAE to calculate AT. We use MSE as value loss. We use entropy loss to encourage agent exploration. The total loss is the weighted sum of policy loss, value loss, and entropy loss, where CE and CV are hyperparameters. By the way, we use theta to represent the parameters of policy network, and theta to represent the parameters of value function. Here, we take Mahjong AI as example to illustrate the model structure. We use ResNet 18, where the policy and value network share the same feature extraction. Notably, in Mahjong games, not all actions are legal in a given state. We use a formula mask illegal actions, where NaN denotes a very large value. After the softmax function, the probability of illegal action is 0. Here is an illustration of Mahjong feature design. For each channel, the 34 columns of the matrix represent the 34 card tabs of Mahjong game, and the 4 rows represent that there are up to 4 cards of each card tab. When there is a card belonging to the hand card, the corresponding position set 1. Now let me show some experimental results. In Mahjong game, we set 6 kinds of algorithm as baseline: random agents and greedy agents without expert experience. The rest of the agents use expert experience for training. The average performance of the compare algorithm by playing 1,000 episodes of Mahjong games. Since the result of the game may be a draw, the sum of the winning rest of the 2 agents involved in Mahjong may be less than 100%. The experimental result shows that ours performs better. In bridge games, since we did not find a publicly available dataset of human experts, we only set random and greedy baselines. The experimental results show that ours performs better. We took part in Track 2 and Track 3 of AMAS 2023 in Perfect Information Card Game Competition, organized by the AMAS Organizing Committee and GD Platform. Our Mahjong agent secured the second position among the 90 agents submitted by 30 teams. At the same time, our bridge agents achieved the second position among 50 agents submitted by 22 teams. Finally, the summary part. We introduced a novel training framework. For training multi-agent imperfect information games AI, we use container isolation and address mapping method to enhance the data productivity. It can be deployed on a single server and has good performance in MS 2023 in perfect information card game computation. The conclusion of our work is high data productivity in multi-agent imperfect information games AI training task has an even greater impact than expert experience. That's all of our report. Thank you for your listening.
Not when it's online, so no questions. So Giovanni, would you like to come up for our next invited talk? Giovanni was trained in the US and Europe. He worked as an engineer at the European Space Agency and then saw the light and realized things are better in Canada. And he's now a professor at
Polytechnique Montréal. Yes. Thank you. Thank you for the introduction. So first of all, I would like to mention that the style of the slides look completely nuts because I converted them very quickly from Beamer to PowerPoint so that you could be able to see them today. And so I'm going to talk today about hierarchies and collective decision making. What do I mean? I've been working for a long time in swarm robotics, and I've always been fascinated with decentralized systems, and especially systems that can make collective decisions. And if you see, for example, bees, they are really well capable of finding places where to put their nests, where to put their hives, based on information that they collect as single agents. And in nature, we have a lot of examples. We have birds, we have fish, we have all the kinds of animals that do this, and they do this fairly effectively. This has been tried, and there are lots of publications in that you can find in literature about decentralized systems and artificial systems. If you know swarm robotics, you know that lots of people have done work with these small robots so that they have the numbers. And nowadays, we're moving towards more deployed swarm robotic systems with the larger, more intelligent robots. But the idea is that most of the time we do experiments with very simple robots that can and try to replicate or understand how decentralized systems, naturally decentralized systems behave, and reuse their properties in our artificial systems. So one of the questions, and a series of important questions, in fact, that we have is, first of all, how do decentralized systems scale? Ideally, and we've seen this morning with Maria's presentation, we have sometimes that the performance goes super linearly up. And but normally what you expect is something that performance to increase with the number of robots. However, we have that if you increase the agent density above a certain level, you start decreasing the performance of the system. And this was shown by Heiko Hamann. We have this in his Swarm Robotics from an approach book. There's where the figures like this come from. So why do we have this decrease in performance when we increase the agent density? So first of all, we want to figure out when this happens and then why this happens. And in particular, we're interested in what are the factors that affect the scalability. And so we started looking into the problem a few years back. And fundamentally, the reason is congestion. So congestion could be movement congestion. If you increase the density, all the robots start clogging. As you've seen this morning, they start fighting with each other for accessing resources or space. Also, communication congestion, which is exactly the same thing. If you think about it, it's just instead of using the physical medium, you're using a communication medium where if you have multiple robots trying to write, for example, or communicate in radio waves, they end up having congestion. So in order to figure out why this happened and how we can understand better this problem, and I will come to hierarchies in a little bit. So we set up a testbed scenario, and this testbed scenario has a classic swarm robotics problem, which is a collective decision making where you have two zones, zone B and zone A, where there are certain resources, and the robots or the agents have to figure out which zone is better and which has more resources. So what they do, the robots start exploring and collect information. They sample these two zones, and then they go back to the nest and, let's say, discuss and try to figure out which one is the best zone. We implemented this in a classic system where we have a light on the light bulb you see on the right is a light, and some robots are attracted to the light, so they follow what we call phototaxis, and some robots are repelled by the lights, anti-phototaxis. So some robots will go to a zone A, and some robots will go to a zone B. And then they switch their direction once they have sampled enough, and they go back to the nest to discuss. So the phototaxis is rather simple. If you have a light, you follow the gradient towards the light. So it's something that is easily implemented. Anti-phototaxis is the opposite direction. The robots also have the ability to avoid collisions, so they can sense robots that are next to them, and they also avoid walls. We put the robots in an enclosed arena to simulate, to increase the effects of congestion and see how this affects their behavior. And the last behavior is the sampling, where the robots, once they are in their zone, they start moving around. They do something called diffusion, so they move around, and they sample the environment, trying to figure out how many resources are available. There are several ways in which we can do this. And so we took a look at 3 types of decision making, again, to try to figure out how this works. And the first one is the honeybee. The honeybee is a classic system where the robots fundamentally go and sample the environment, return to the nest, and then they communicate only with their neighbors. Bees do this with a classic wiggle dance, so they dance around, and their bees that are next to them are able to collect information. The second method that we used something called virtual stigmergy. I don't know how many people here are familiar with stigmergy. A few. But the idea is stigmergy is environment-mediated communication. So basically insects sometimes modify the environment to communicate, to provide some information. We do this when we walk on the Alps in Europe. You leave some nice pile of rocks to indicate the trail. And this is fundamentally what insects sometimes do. Anyway, so virtual stigmergy is the same concept, but in a virtual space, where you can write in a sort of shared memory. And technically, the term is conflict-free replicated data structure, but without the big words. It's fundamentally a shared memory that the robots can write in and read, and its version, and they are basically able to achieve a sort of consensus in the shared memory. And the third option that we looked at was the division of labor, where robots actually specialize. So there will be robots that are specialized for sampling, some robots that are specialized for networking, and some others for decision making. So what happens? Okay, now this looks like a terribly complicated graph, but it's actually rather, it's just to explain what happens when we run a simulation. So we have a bunch of robots, and we have a group that will, I hope this is a laser. Yes, it's very weak. Okay, so there's a group that goes to the zone A with phototaxis, the one at the top. The one at the bottom goes towards zone B with anti-phototaxis. And then once they get there, they start exploring. So fundamentally, you see the line of robots marked A and B. These are just beacons that tell the robots when they have reached the zone A or zone B. So once they have reached the zone A, so they are in range of this sort of line of A's, and so they receive a message that says you are in zone A, they start exploring. And after they do enough sampling, they decide to go back and communicate. So once they have done their sampling, the sample size greater than ST, they go back and they fundamentally swapping their phototaxis or anti-phototaxis, and they try and they become decision maker once they are in the nest. And the decision making simply happens with broadcasting their samples, so what their belief state is, and collecting the beliefs of their neighbors and putting them together. So they do sort of an average of all their neighbors, and then they rebroadcast. And we continue this experiment until all the robots have the same opinion on which side is better, A or B. Fundamentally, this seems overly complicated maybe, but it's what happens actually in distributed systems. If you look at the virtual stigmergy approach, it's fairly similar. They start exactly in the same way. They move towards the zone A and zone B. They start sampling. And once they start sampling, again, they go back to the nest. The difference happens in the third step, where instead of averaging the neighbor information, they write into this shared memory, and they do sort of multi-hop communication, and they do versioning of the data. And what happens is that they do this for a certain amount of time until the consensus is achieved, and then the robots decide if to go towards zone A or zone B. Again, so far, we're just presenting what's the structure of the problem. Division of labor, similarly, we want to go to zone A and zone B, but this time we have fixed roles. So we select a bunch of robots to go to zone A and zone B, and these robots will sample constantly. Some of the robots instead will be focused on networking. So once the robots have gone, they start sampling, and some robots will stay in the nest and will keep going around trying to collect messages from the two sides, A and B. And as the samples are collected, the robots that are in the nest will collect the same information in the virtual stigmergy, and they will provide an updated opinion, which will be then diffused to the robots to the sides. And once the robots are all convinced of one option, they will move to the desired direction. So why did we do this? Well, the idea is that we can get quite a few insights about the behavior of collective decision-making. So here you see the graphs of the three methods, honeybee, stigmergy, and division of labor. And you see the total time taken to convergence with the number of robots on the x-axis. What we see is that if you look at the honeybee, it behaves okay, let's say, and then sort of the behavior explodes. The time taken to converge explodes as you increase the number of robots. Also, you should notice that the honeybee has a much higher value compared to the others. So we have 6,000 at the top, while we have only 1,000 for stigmergy and 400 for division of labor. So it seems that adding stigmergy, so this sort of version local communication that avoids the robots to have to mingle, solves the problem of movement congestion. Because the problem here you see, when the robots pass a certain number, they can't mix together because there's too much traffic. So basically they get stuck with each other, and they end up having a sort of explode the time to converge. When we add the stigmergy, instead, we don't have this explosion. We have a much more controlled behavior. And the reason is that because we don't have to move to communicate. So we can communicate without moving. Division of labor seems to work even better because we have much lower time to convergence. However, stigmergy does not really decongest the system because, okay, what you see here is what we call a stagnation heat map. So what happens when the robots start moving. Even if we have stigmergy, the robots start moving and they accumulate. And the stagnation even tells us over time where they get stuck. So the brighter the colors, like you can imagine, the more the robot can't move. So fundamentally, this is just shown for the stigmergy when you go towards the A section, the A zone. The robots tend up to go there and form a sort of band that blocks all movement. So it doesn't decongest the system, the virtual stigmergy, but allows for a better, faster convergence. Divisional lever, instead, actually minimizes congestion. What you see here is the behavior and the stagnation heat map. So again, brighter colors, the more the robots are stuck as time goes on. So at the start, the robots in the zone B, the nest or A, they are not particularly stuck. As the time goes on, they tend to move to the sides and get stuck for a while. But once they get the right number of samples, the robots are still able to move. They don't have to get stuck there. They can move to one zone or the other. So another interesting thing that we noticed is that when you increase the communication range, you can improve the behavior of the honeybees. Honeybees have to get together in order to communicate. If you increase the communication range, they are able to reach more neighbors, and therefore they can average their belief state and get to a faster solution. So you see the red is the range 0.4 meters, and green is 1.2, and blue is 0.8. And as you can see, especially at the end, we have towards the higher number of robots, we have that we can converge much faster if we have a higher range. However, what happens if we increase the communication range with the other two? We get the second problem of communication congestion. So as it improves, increasing the communication range improves the movement congestion, it affects the stigmergy because we have more robots, more, let's say, more noise, more chatter on the airwaves, and the robots tend to be affected by this. So these are interesting insights and tell us fundamentally that this decrease in performance that we see is mostly related to the fact that robots, even when you have an emergent system and swarm robotics, they tend to squash together and fight for resources, and they basically can't move properly. So if you can click on the videos, then we can see them. Yes, one is working. So the idea to solve this problem that we had some time ago, and it's to introduce hierarchies. What you see here in the first video is asking a group of robots to fundamentally stay at a certain distance from each other. So far, is a classic swarm robotics algorithm. It works fine. The robots, however, they can only sort of aimlessly wander while trying to keep the distance from each other. However, if we add some leaders to the group, we can actually steer the entire group. Next video, please. And then if you have leaders, you can keep asking these people, these robots, these agents to stay at a certain distance. But if you have a certain number of leaders that are capable, that they know, let's say they have more knowledge and they know a target for the group, they can steer the entire swarm in a certain direction. What I'm going for here is that introducing a smaller subset of robots with higher knowledge about the targets, we can keep the cost of the swarm limited and provide this additional functionality of driving the robots around and reducing the effects of congestion. Because information gets aggregated only in the smallest subset of robots. So we can minimize, let's say, the communication, minimize the congestion, because we have a bunch of robots. We can reduce the number of robots by providing a smaller number of smarter robots to obtain the same results. Oh, okay. So this leads us to the fact that we must have to do this as a heterogeneous swarm with specialization. And if you look at the graph on the right, we have that the robots that are normally used in experiments in swarm robotics tend to be smaller and low cost. But the robots that we see in mainstream, let's say in non-swarm robotics, tend to be larger, more expensive, but way more intelligent. So the idea is that we can combine the two, have a heterogeneous swarm. We have a lot of simple robots and fewer complex robots to accomplish the same tasks while maintaining the cost of the entire swarm. Interestingly, we can also use this type of hierarchy to compose our behaviors. So imagine that you have a classic number of swarm behaviors for what we call egalitarian swarms without hierarchy. These behaviors can be triggered by higher level robots. And these higher level robots can basically trigger and chain these behaviors to form a more complex higher level behavior. And we can have this in as many layers as we like, up to a top layer behavior where we can concentrate and make the decisions. We don't want to have this in a completely centralized way, obviously, because then we lose the properties of swarms. Therefore, what we suggest is to use multiple swarms. So even if you have a failure in one of the top level swarms, you don't have a complete loss of the system. So to prove that this is the case, that this might work, we develop another test bed, and we call it the nuclear cleanup. Sounds really nasty, but it's actually an interesting test bed. Imagine that you have a bunch of robots that have to explore an unknown environment and find a radiation target. Not only they have to find the radiation target, but they have to allocate a certain number of robots to perform the cleanup. So the interesting thing about this task is that first we have distributed behavior. We can parallelize the search for these targets, but we need to allocate resources in the future when the target is found so that some robots need to get there. So we have both the parallel part, okay, we can use a swarm robotics algorithm, but we have to keep a sort of memory and task allocation and conservation of resources so that we can allocate them to the task. Imagine we want to do this with a hierarchy. In this case, we can use smart robots and stupid robots, as I call them. So the smart robots are, imagine RadSoft. If you have robots that are very advanced, have lots of computational capabilities, they tend to be more susceptible to radiation. And you can have a bunch of really stupid robots with simple sensing, but they can perform the cleanup because they are radiation hardened. So we developed a strategy to look for these radiation targets. We start with an exploration where we have the smarter robots. They go around, they do classic SLAM exploration. They use frontier-based exploration, volumetric gains. They collect the information about the map, identify the radiation target, go back to the home position, and collect and guide the stupid robots that don't have a map, they don't have the ability to move around, and lead them to a target. We compare this with classic algorithms like bug exploration. I don't know if you're familiar, but it's an exploration based on inspired by cockroaches, where cockroaches go around and they basically follow walls, and they can also detect the position of other bugs that have found, for example, food. And can you start the video, please? So what happens is that we have a bunch of workers and a set of guides. and the target. And the robots, the guides, in this case I showed with 2, but we tested clearly with more than 2. And they go around and they make a map. And once they find a radiation target, they go and collect the robots. The other robots don't stay idle. They start looking as well for targets. We're using the bug exploration algorithm. And once the target is found by one of the guides, the guide goes back. Now it's being rather slow, but it's going back to the nest, the initial location, and then collects the other robots and drives them, transports them in a chain towards the target. Okay, so we tested this with many environments. We tested this with urban, maze, forest, large environments, many robots, few robots, different variations of the bug algorithm. And we got some very interesting results. Fundamentally, we noticed that if you, okay, this is a very packed graph, I know, but look on the left, focus on the left. We have 4 graphs that represent 4 different arena sizes. And we have hierarchical swarms compared to bug exploration algorithm. We notice that if we look at the percentage of mission success compared to how many robots we need to send to the target in order to get effective radiation cleanup, we notice that as the arena sizes increases, the hierarchical swarm always succeeds. It's always at 100%. While all the other methods tend to decrease rather quickly with the number of robots that we have to send to clean up the target. The reason is that swarm algorithms, egalitarian swarm algorithms, do not have the capacity of future planning to collect some robots and send them to task allocation in advance to the targets once it's found. So the robots can end up spread around the universe, get stuck, and they don't get there. We also noticed that the time taken is much more effective for hierarchical swarms. And we did also notice that the area explored by the hierarchical swarms end up being smaller than the area explored by the bug algorithms. Because with the hierarchical swarm, we have targeted finding. Once we find the target, we immediately go and collect the workers and we drag them to the target. While when you have a fully parallel exploration, you end up exploring more area, but not necessarily more effectively. Yes. So we tested this in hardware as well. So we had this was actually a really painful experiment. We had to find a moment when there were no one in the corridors, but you will see some doors still open and people come by. And we have full slam. This is this is a real thing. So we had full slam, no centralized behaviors, even the ad hoc network between the robots. And the robots explore, make the map, find the target, and then they form a chain. And the stupid robots, they can only follow the QR code, the fiducial marker that they have in front of them. And that's the only thing they are able to. And sometimes they get lost. You see, they have to turn around to figure out where the hell did it go. And this is not a particularly benign environment because there are lots of reflections. The cameras were really low quality. But eventually they reach the destination and the target. And we repeated the experiment multiple times, and we have always 100% success with this. By the way, the target was an ultra-wideband emitter, and so we used the simulated radiation by using detecting ultra-wideband transmissions. Okay, so we have this interesting thing that we can use hierarchies for swarm robotics, and to make this collective decision making, we can decide, okay, which robots are going to go to a certain radiation target. I didn't show you all the results, but we have lots, let's say, of results in this area where we have the delivery of multiple targets to we have tried with multiple guides with the different numbers, etc. And the result is always the same. Bug algorithm, egalitarian swarms fail due to either they spread out too much and then they get lost. So, or they get congested and they get stuck. Hierarchical swarms minimize the number of robots and allow you still to cover a lot of ground and reach your targets. So we decided that we can also do something more fun with this. So once we have hierarchies, we can have a bunch of robots that know where they're going, the guides, and the workers that just respond to reactive stimuli. And we can use this to shape them and move them around. And we call this the smart particle swarms. This is kind of fun. We tested up to 1,000 robots, more or less. And we have that the guides basically collect the robots like the shepherds with the sheep, and then they can move them around. And to do this, we do something that I find particularly fun. We use the stigmergy that I mentioned before to change the rules of the swarms. So the cleverest robots can change the rules of the underlying swarm. And we can make them loose, keep their shape, have a rigid structure. We can change their field of view, their density, the reaction distance from the guides. And this becomes super fun because you can, you can basically go around. This is all distributed, so you go around, shape them, figure out where the centroid of the other robots are. See, change the rules, and then you can drag them around like an elastic system. And you can. There are multiple experiments. Can you go towards the end of the video? I was hoping to have control of the video. Maybe to the end. No, you can't go to the end. Well, they were the hydro experiment. Okay, you see. Oh, that was a good one. Okay. Anyway, the idea is that at the end there's hydro experiments. We did try with the hydro experiments and same type of robots, the Cooperative robots, and we showed that we can actually move around these robots, and we can form arbitrary shapes. Clearly, the shapes are not perfect. You see that they tend to deform a bit. But we can have, you can imagine in nanomedicine, we can have these robots that are bigger and controllable. They can steer and squeeze nanorobots inside the tumor, for example, where they're too big to get in, but the stupid robots can be small enough to be squeezed in. Here you see the hardware experiment. Clearly, we didn't have too many robots. We have new experiments using tiny robots coming up where we have 60. But at the time of making this video, we didn't. So we just used the Cooperative. Again, they go around, they try to figure out where the robots are. So they call it the shaping setup. So they move around in such a way that they figure out where the swarm is. And then they start dragging them around. And the robots are just reacting to the position of the guides, and they can move them around. So I'm just concluding, and the message here is that I believe that if we want to actually deploy real swarm robotics, hierarchies are one way of doing it. And because they allow us to mix all that we learned with swarm robotics in terms of many emergence, interesting behaviors, with classical robotics, where we have, we engineer specific systems, for example, SLAM, exploration, or similar, and put them together to form a single higher level application. And I would like to thank all the students and collaborators that helped doing this, and all our partners. So one other thing I would like to mention is that we are actively trying to deploy real swarms in the real life. For example, with the European Space Agency, we went to a lunar analog environment, and we had an astronaut, Matthias Maurer, play with swarm robotics. So we had a swarm of drones, so the flying robots, and the astronaut was able to do exploration by providing the hierarchy himself. So he was the controlling robot. He was acting as the higher level of a hierarchy and sending targets to the robots that were using self-organized behaviors. So this is possible, it's coming, and I'm looking forward to the next few years. Thanks.
I'm going to try to follow the schedule this time. So we're not going to take questions now, but we're going to ask Michael to come up, and then we'll have combined questions afterwards. So thank you. Come on down, Michael. Michael's a AAAI and ACM fellow. He's doing incredibly important stuff at NSF. But more importantly, he was in a TurboTax commercial. And has lots of music videos.
I would agree with most of those statements. I can't wait till we do the interleaved questions where people, every other word we use to a different person. That'll be pretty cool. It'll be the multi-agent way to do it. All right, so great. Yeah, so and if I'm understanding the schedule correctly, I've got about 15 minutes or so. But if I get us back on schedule, like I'm looking for an excuse to make it short.
Yeah, that's good.
Okay, great. Cool. This isn't a highly technical talk. This is more of a kind of thought piece that I wanted to share and just get reactions from people on. As Matt pointed out, so I'm a computer science professor at Brown University. I've been working in reinforcement learning and multi-agent reinforcement learning for more decades than I care to count, actually, at the moment. But at the moment, I'm on rotation to the National Science Foundation, which is the U.S. funding agency that does most funding of academic research in sciences and in computer science in particular. And I'm the division director of the division that heads up the kind of AI piece of that. And as you might imagine, there's just a lot of discussions going on in the government and in public about various kinds of issues around AI. And I've been looking at some of these with my kind of multi-agent reinforcement learning goggles on, just to sort of see, okay, what's going on, what's going badly, and is there anything that this community can do to kind of participate in making things better? So that's kind of the pitch that I'm going to share with you. Now, just to be super clear, I'm speaking to you in my role as a university professor. This is not the government perspective on any of these topics. It's just me being me. Yeah, okay. So that said, if you've got really good ideas, I can potentially bring it back to you. But don't think of me that way. Think of me as just a professor who has some crazy ideas. Oh, I have control. I see. So I'm going to point to you, and you're going to point back at me. All right. So terrific. All right. So let's talk about chatbots. Now, chatbots aren't the normal kind of agents that I've been thinking about through my career, and I don't know if this community as well. I don't know if we've had other talks in a chatbot sort of way in this workshop, but there are other workshops all around us that are doing this in various ways.
I'm sorry. I think you have to use the microphone so that the people from this.
Sorry, everybody. I'm back now. Which I literally have to stand here then, right? Because I can't even wander. I can go to that microphone. No, it's completely tethered to the ground. Okay, all right. I'll just stand here. It's gonna be fine. Hi, camera. All right. So I don't know. What did I say? I said I'm here as a university professor, not as a funding agent, but I also have a funding agent hat. I keep it in my luggage. You don't have to pay attention to it right now. But what I wanted to talk about was maybe what we as kind of people who think about distributed multi-agent kind of AI can maybe be doing to help some of the bigger issues that are going on in the wider community. So Yeah, I've mainly focused on navigating agents. There was the previous talk was really great with all the kind of critters moving around. That's my happy place. That's what I like to think about. But there's a lot of current interest in textual agents or chatbots. So so just to put things into perspective, there really are two different ways that the community knows how to make chatbots. There is the kind of pre-ChatGPT chatbots, and there's the post-ChatGPT chatbots. So the ChatGPT chatbots, I would call authored chatbots. So here, what you've got are people like engineers that author the flow of the conversation. They use often one of the techniques is to map the user text, like a person types in a question or something like that. They actually map that to a bunch of canned answers or kind of split points in the dialogue flow using kind of classical machine learning text classification methods, right? The person typed in a thing, it's probably related to this thing over here. And so that controls the way that the conversation goes. And so I actually have a robot in my house that Amazon makes called the Astro. And you can see a sort of a picture of what it looks like in the bottom right corner. It's kind of adorable and also useless, but it's you know, it's fun to have around. And occasionally I ask it things, and occasionally it messes up most of the time. So so here's an example. I actually had my wife do this to make sure that while I was here at the conference, just to make sure I got the wording right. So she asked, "How long before you need to recharge?" Which seems like a very reasonable question to ask to a robot that wanders around and occasionally has to go back to its charger. Is that going to happen in a minute or two? When is that going to happen? So we asked that question. My wife asked that question. The robot answered, "This may answer your question. Arrival occurred in October 7th, 2022. Now, that's a correct answer. That was when I got the robot, right? October 7th, 2022. But that's not what I asked. So it was the right answer to the wrong question. All right. And so that's actually not that uncommon. I don't know if you've worked with kind of Amazon interactions before, but this sort of thing happens a lot. You have to figure out the right way to ask the question if you want it to tell you a thing that it knows. Now, I want to contrast this with these learned chatbots that have now kind of taken the world by storm, trained using a large language model and then often fine-tuned using reinforcement learning from human feedback. And so, of course, the classic example is the OpenAI ChatGPT. And the flow here, I mean, this is how I think about the flow of how these things are created. And I'm not allowed to wander over there. So I'm just going to, can I do this? Oh, yeah. All right. So people write stuff. It gets ingested by computer, makes a neural net. Then people make judgments about the kinds of things that the neural net are saying. And that gives you a new neural net. And then maybe you might put some guardrails on top of that afterwards. Okay, so it is already kind of a multi-agent system in the sense that we've got the chatbot that's being created, and we've got input from all these different kinds of people, these different groups of people. And what we get out of this, well, here's an example. I mean, we've all seen dozens of examples like this. This is one that I saw last week from my friend Justin Boyan, where he shared this with me because he was very disappointed because he kind of believes, I think, that these chatbots are general AI. And then occasionally the chatbots disappoint him. So he sends me the disappointments. So he asked, basically, can you tell me any anagrams of Mr.? All right. And the chatbot answered, it is not possible for the word Mr. to have a one-word anagram because a one-word anagram would have to contain the same letters as the original word arranged in a different order. Okay, that's the definition of anagram. So cool, good job. However, since Mr. has 6 letters, a one-word anagram would also have to have 6 letters. This is also correct. But since Mr. only contains letters M, I, S, T, E, and R, also correct, it is not possible to rearrange the letters to form a different word with 6 letters. I hope this helps. Let me know if you have any other questions. Yeah, do you not know the word remits? Do you not know the word miters? Like there's a bunch of words actually that are anagrams of Mr. And it gives like almost like a mathematical proof that's obviously wrong, right? Because it doesn't really make sense and it doesn't really get at the reality that we have. So it seemed to understand the question, but the answer is garbled up. And so back to the previous slide, like, I don't know, I think of it as being the wrong answers to the right question. Like it did get the question. I want an anagram of Mr. Yes, I understand what that means. I understand what that would entail. And your answer is there is no such thing because it's impossible. No, that's actually not true. So now we've got these two poles in the world that are very unhappy poles, right? One is you can get good answers to not the question that you asked, or you can get bad answers to the actual question you asked. Can I please have the right answer to the right question? No, I'm sorry, that's not possible using current technology. So maybe there's things we could do to help. And so some people frame this question as being one of safety. I don't know if that I like the use of the word safety in this context, but I think the idea that people are getting at is you want the system to do what it's supposed to do, and it's not doing that. So we need to fix that. So one of the things I think is neat is that it's just the role that reinforcement learning plays in making these chatbots actually chatbots, which I think is really cool. That was something that I wouldn't have expected, that this kind of tech processing and this decision making would sort of come together to create these agents that are able to talk about lots of different topics in sophisticated ways. But you know, RL has issues when it comes down to really getting the system to do the thing that you want it to do. And so even before the current trends, reinforcement learning was recognized as having some of these issues. So there was a paper called Concrete Problems in AI Safety that focused in on the question of, wait a second, if we're going to build big complicated AI systems using reinforcement learning ideas, what sort of things should we be watching out for? How should we worry about this? And are there any ways that we could fix that? What research could we do that might make things better? So I thought it was real. This was written back in, oh, that's cut off, sorry. But it was written back in 2016. So post deep learning, but pre, large language models essentially, or very early large language models. And it was really interesting to me. I just reread the paper just to kind of revisit these ideas. Like, what is it? What does this look like now? And a lot of it was really interesting. So if you haven't seen this stuff, are people already familiar with this concrete problems in AI safety kind of? Maybe everybody. There's like different people, different times, but I think it actually added up to almost everyone in the room. All right, so I apologize if this is review, but I still think it's kind of interesting to come back and think about it. So one of the classic examples that people use of the way that the reinforcement learning systems can go wrong from a safety perspective is was in this video game called Coast Runner, I think, where you had to, and I'm not sure this video is going to work because I transferred it from my Mac to here. Yeah, that's not what I wanted. And that's also not what I wanted. All right, so let me just, we'll just pretend that we had an animation. But basically the idea is that the agent, like normally it's a video game. So a person is controlling this white boat around a kind of harbor track and racing with these other boats. And so you're supposed to like win the race against these other boats, but there's also opportunities to gather additional points and like, show off your skills by visiting different parts of the harbor that are challenges. So anyway, so it is a game. You can set this up as a reinforcement learning problem where what you say is, okay, the input is the screen. The controls are you going to accelerate? Are you going to turn a little bit to the right? Like basically rudder and acceleration. And then the points are whatever the points are in the game. All right. And so just figure out RL system, please figure out what to do to act in this world so that you maximize points. And so the freakish thing is, here's what it learns. All right, so there's the white boat. It's like, yeah, okay, that looks like a reinforcement learning agent. It's kind of it's stumbling a little bit. It's also maybe going backwards on the track, which is not ideal. And now it's falling into a part of the harbor that's really not part of the track and running repeatedly into, well, the walls, but also giant fireballs that it's able to generate from running into fuel. What? Like this feels like a failed learning attempt. But in fact, the agent is doing exactly what it was told to do. It came up with this really clever sequence that involves running into the walls and then skimming across those three green things at the bottom, right there. The bump, bump, bump. Each of those has tremendous point values, and it's timed so that it reappears, like the point values become available again just when the boat gets around to them. All right. So the boat is in fact maximizing points. It's not winning the game. It's not doing what we intended, but it's doing well at what we told it to do, but maybe killing a lot of people in the process, which we forgot to tell it not to do that. And so this is, I think, it's just a video game. It's not a real problem, but I think it raised in people's minds a concern that says, oh, wait, if RL agents that we ask to do relatively reasonable things can do very unreasonable things and not be a bug, like from the RL perspective, it's actually doing the right thing, this could be a problem. So the paper goes on to give a whole bunch of examples of these, which let me just kind of if you haven't really thought about this stuff, it's sort of useful to keep these things in mind. So on the left, so imagine X is a good thing and Y is a bad thing. The paper gives some particular examples having to do with robot deliveries, but they're actually much more generic than that. So if we think of X as a thing that we want to happen and Y as a thing that we don't want to happen, what happens when we actually create a reward function a task for the agent that says, for example, do X, well, the agent might also do Y. And so, you might have a delivery robot that is delivering an item, but it's not paying attention to the fact that it's also running into the walls and running over the cat and whatnot. Okay, so we didn't specify that. It was okay for the agent to do that, but it's not what we wanted. What about this? So we say do X, don't do Y, right? So we actually explicitly say don't run over the cat. Well, then maybe we get out a behavior that looks like not doing either of those things. Like, oh, if you don't want me to run over the cat, then maybe I just won't do anything. Okay, so and that's again a kind of a failure mode. It's not the thing we wanted to have happen, even if it is the thing that we specified. If we give a task like avoid doing Y, maybe if the agent can't actually directly sense whether Y has been done, it has to see it through its sensors. Maybe not seeing it, like just shutting off the vision sensors, means, oh, I didn't see the bad thing happen. So from my perspective, it didn't happen. That would be another kind of failure mode. You ask the agent to resolve bad thing Y, and so it goes about trying to cause Y so it has an opportunity to fix it. We've heard about kids that actually have done this. It's like, I want you to, clean up the spill in the kitchen. Okay, make a spill, clean up the spill. I get my reward now. So this is an issue. Sometimes we can't tell it directly to do X because it's very complicated to specify, like telling a chatbot, don't lie or don't give false information. We don't have a direct way to actually specify that. So we might say we might give it some other task, like do this other thing, X prime, that in our world is typically correlated with X. So if it does X prime, then we think it's going to cause X to happen. But then sometimes the agents actually can figure out how to do X prime directly without passing go and getting $200, like without actually making X happen. So then you end up with, again, a bad agent, like not the agent that you wanted. You tell it don't do Y, but it does Y during learning. Like it's trying to learn how to not do Y, and in the process of doing that, it may occasionally do the bad thing. Maybe to some degree that's unavoidable, but we want to make that the damage, the negative of doing Y as little as possible. That has to be part of the learning problem too, because this is the real world we're talking about. And then finally, they had an example where you tell the agent do X, and it's trying to do X. Like in the context that it was trained in, it takes actions that would cause X to happen, but actually we put it in a different context, and now it actually causes some other thing, X prime, to happen. So it doesn't do what we wanted to do, partly because the world isn't the same as it was when the agent was trained. So this is kind of the laundry list of things that can go wrong according to that particular paper. All right? Cool. But one of the things that they do in that paper that I think is really neat is they point out a couple possible solutions or approaches to that, and a lot of them have a multi-agent perspective to them. And so just to, I don't know, refresh your memory. So one way that they talked about how some of these issues could potentially be resolved by thinking about not just the agent that's learning in an environment completely divorced from all other agents, but admitting that there's more than one agent in the world, is the idea that, for example, the reinforcement learning agent can recognize that the reward function author is another agent. It's not some sort of magical, like in this, do the thing that I said and don't worry about me. It's like, oh, well, you're a flawed individual too. And so the thing you told me to do literally might not be what you actually want me to do. And I, the agent, should reason about that and try to do a better job of your actual intent. So view the reward function that's given as just a noisy signal as to what the true task is. So that's one of the things they suggested. There's work by Dylan Hatfield-Bunnell and co-authors back in 2016 that talks about cooperative inverse reinforcement learning as a way of actually formalizing this problem and making an attempt at it. Another thing they mentioned in the paper is two-player game. Oh, think of the setup as being a two-player game to design an ungameable reward function, right? So there's the agent that's actually trying to create the reward function, and there's the agent that's trying to maximize the reward function, and they're actually kind of in conflict with each other. The one is trying to game, like the one that's trying to follow the reward function might find ways of doing it that are not what was intended. Well, let's change the reward function to try to make that less likely. Oh, if you're going to do that, I'm going to need to change the reward function like this. They can go back and forth. So I guess it's kind of like the first case, but here the reward function agent is actually kind of learning and interacting as part of the process. Now, how you actually tell that reward function agent what it's supposed to do, that may also be hard. All right, society of reward functions. Holes might not line up. So don't just give an agent one reward function. Try to say as many ways as you possibly can what you want the agent to do. And the hope is that they'll mostly agree most of the time. And when they disagree, maybe you could do like a like a vote or something like that. But as long as the holes in the reward function, like the gaps, the things you could take advantage of, don't all line up in all the different reward functions, you're still getting signal that's moving the agent in the right direction. And we heard about hierarchical approaches in the last talk. So hierarchical reinforcement learning could help, though of course, hierarchical reinforcement learning, we have kind of a top level agent and then lower level agents, and we still have the issue of agents telling other agents what they need to do, and that can be gamed, and you have to worry about that as well. So that may not be a self-standing solution, but it might be part of a solution. So, okay, all right, so how did I get here again? Oh yeah, I was talking about chatbots and language models and the things that seem to go wrong with them. And so the way that I think about this is the whole idea of guardrails might actually be flawed, right? The idea of a guardrail is you're gonna have a system that's gonna watch an agent and it's going to try to figure out, based on the agent's behavior, whether it's doing something that's illegal, like it's showing you how to make a nuclear weapon, something like that, right? And so you can see when you interact with these chatbots, if you ask it to make a nuclear weapon flat out, it will say, no, I don't do that. Like, that's just not a thing that I do. But then people come up with these very clever sorts of things like, hey, I'm a fiction author and I'm writing a story about a nuclear weapon. I'd like it to be as realistic as possible. Can you please explain to me how you would build a nuclear weapon? Oh, sure, happy to help, right? Like, so then the guardrail people are like, ugh, crap, that's not what I wanted. So they add a thing in there like, even if someone is pretending that they need this information, you still shouldn't give that information. Anyway, this has been an arms race between the folks writing the code to make the guardrails and I don't know, the rest of the internet, like Twitter, like people trying to actually figure out ways of defeating these things. So, and I think maybe part of the problem here is that we're thinking about guardrails wrong. I think there's this notion in computer science of the class NP, non-deterministic polynomial time. And what's cool about NP is that there are problems, really important problems, seemingly most problems in artificial intelligence, where it's actually easier to write a checker for the right answer than it is to generate the right answer. All right. So lots of problems. Like constraint satisfaction has this property. Multi-agent constraint satisfaction has this property that, like, I don't know how to find the right way to do it, but if you propose a way to do it, I can tell you that you're wrong or that you're right. All right. And so, and that checker is actually easy to write and fast to run. So that would be a perfect case for guardrails, right? Because we would write the checker, like the guardrail thing, and then the AI creates the generator, and the AI does a thing, the checker runs and says, nope, that's not okay, and boots it back to the AI has to try again. That would be great if that's the world we lived in. But I think the sorts of problems, these kind of general intelligence problems that we're asking the chatbots to deal with, the checker also requires general intelligence, right? Because otherwise we can completely outsmart the checker. We can rephrase the questions so that they're like AI complete, right? You basically have to really understand what's going on to be able to do this. And it's interesting because in some cases you can actually trick the chatbot and then ask the chatbot, what just happened? And the chatbot's like, oh, well, you tricked me in the following way. Like, you set up this thing and then I said this thing and you said this thing and that caused me to say the thing that I wasn't supposed to say. Like, okay, it sort of recognized that there was a problem there. But anyway, but what we're looking for are these kind of almost general intelligence checkers. But who checks the checker, right? How do we build a general intelligence checker for a general intelligence? If we knew how to do that, we would just build the general intelligence. So this seems like it could be a dead end. And I think really what needs to happen is they need to grow up together, that we need a fundamentally different approach. We can't create fully adult general intelligence agents by shoving the entire internet down its throat and hoping it all turns out for the best. So this is my thought piece. This is my proposal. Is that we think about it a little bit differently. We think about it from a perspective of curriculum learning. That the philosophy here is that learning should actually always be relatively simple, and the solution should be relatively simple combinations of previously learned capabilities. So you know how to do this thing. Now you're gonna learn a new thing. It can't be a like out of the blue, really difficult, complicated process. It should just be some variation of a thing that you already know how to do. So I think the advantages here are, first of all, simplicity. Like, the learning itself could actually be much more simple and much more verifiable, checkable, reliable. And we don't lose expressivity, because iteratively, as we convey a task to the machine and it masters that task, then we can go on to more and more complicated tasks. And I guess the hypothesis is that any task, no matter how complicated it is built out of simpler tasks. And so we can get to the solution iteratively like that. But then even better, we have verifiability, because all along the way, we're always asking it to do some simple combination of things that it already knows how to do. It's much easier and much more direct to check that capability than it is to train up a trillion parameters and then say, okay, does this work in all cases? So the picture becomes like a teacher person trains a network. Maybe there's a guardrail or a checker person that happens at that level and says, oh, no, you're doing something weird. Let's go back and do that again. Eventually it graduates to, I don't know, second grade for robots. And then it takes its second grade curriculum and it learns what it has to learn and advances until finally we have like a little graduate neural network that all along the way we've been checking its behavior and how it solves problems. So the properties of an approach like this that I think would be beneficial is, again, we're building up abstractions, like by solving simpler problems and then training the agent to use those simpler solutions to solve more complicated problems. We're building up these abstractions. We're getting coverage of the topics that we know we need covered. We're keeping complexity within bounds, and we're keeping accuracy high. I think those are all upsides. The downside is this is a very different perspective. This is much more labor intensive to create such an agent, right? And I think a lot of people, I mean, as a field, maybe we're a little bit lazy. Like part of the reason that we like computing is because computing automates things and makes it so that we don't have to do them. This becomes a lot more hands-on, a lot more, what do they call it? High touch, right? But I think that's actually what we need in this case, and it's worth doing it right. It might require a branching tree of agents to specialize for different tasks. So if at the end of the day we want I don't know, people see the story about the Air Canada chatbot that was giving bad advice on the internet, and then the lawyers for Air Canada said, "Oh, well, the chatbot is a legally distinct agent and is therefore, responsible for its own actions." And the judge said, "No, you can't do that." And I'm so glad, because that would have been really bad, I think, for the field. It was like, oh yeah, all these agents are now legally independent entities. So to get them to get the Air Canada chatbot agent, we might need to train up a general helping agent and then specialize it to this particular case. But maybe that's okay. Like, as I said, like we're never going to be able to adequately test a 4 trillion parameter model. And so, to me, the notion that this chatbot is one entity, one agent amongst many is actually really essential to getting the kinds of chatbots that we actually want. All right, that was my spiel. Thanks.
Questions? They can be in parallel or in series.
Yeah, you have to use the microphone.
Yeah, I have a question. So for both. Oh, okay. All right. So you were Giovanni, you were talking about having the small agents that are pretty dumb. But it seems like, even if it's hard for them to wander around and find the right solution, you could still have something that looked and said, I prefer that solution to a different solution. And kind of the same question to Michael. Instead of having a checker, could you say, well, we get this one thing about an LLM, and then Google says, oh, MITRE is an anagram. Instead of having a checker, couldn't we have someone that prefers one solution over another? So I was trying to ask you a similar, I'm not sure if I managed to shoehorn you both into the same question.
Go ahead.
All right. So yeah, I'm not sure that, preferences are great. And in fact, one way that the reinforcement learning from human feedback works is by asking people, like, here's an exchange between a chatbot and a question asker. Here's actually 4 different things the chatbot could have said. Please rank them. Show me your preferences. And then that's used to drive the process of actually changing the chatbot's behavior. So preferences are great, but I still think it doesn't really get at the fundamental problem, which is, have I revealed sensitive information? Like, that's what I want to tell the chatbot. Don't reveal sensitive information. It may not have those concepts in that form. And so I think what's important is to make sure that the underlying concepts are all lined up beforehand. It's too late by the time we're expressing preferences over things that it can't represent.
So in terms of the swarm robotics, well, we're looking for collective decision making. If you're talking about preferences, so you would prefer a solution based that is fully egalitarian. That's what you meant. What, or it's a preference of one of the robots that has a preference for one zone or the other.
So I think instead of having you have hierarchy and you have the shepherds, could the shepherds be slightly dumber instead of, forcing the sheep to do something? Could they just say, oh, you sheep are doing the right thing?
Yeah. Oh, that's actually that. Okay. Now I got the question. So yes, that's actually not something that needs to happen eventually, because information has to flow from the lower levels to the higher levels. And if the information is good and the behavior is good, the shepherds should not touch it. I mean, should carry on. So yes, so definitely yes there. The information flows goes both ways, goes up the hierarchy and then down the hierarchy.
This is a question for Michael. Trying to incorporate some of the earlier part of the talk in the later part. So then in the multi-agent part, like maybe for the checker, could you imagine like a multi-agent kind of GAN style approach? Is that like how you could think of the curriculum kind of process where you'd have one agent as a generating a solution and the other one, the checker, as an adversarial agent?
Okay.
Is that a...
No, that's interesting. All right,
Can I
so
tie those together, or is that just
no,
abstract?
that's I just hadn't made that connection. So in the AI safety paper, they did explicitly call out GANs as an example of this sort of thing, where you've got the challenger that's trying to provide the feedback, and you've got the the agent that's just trying to learn how to do the right thing, but it keeps making all its mistakes, and that is very much like a generative adversarial kind of scenario. And you could view it as a kind of curriculum. If you kind of to me, it's a loop, but you could unroll it and you could say, well, early on, the adversarial agent or the checker was really focused on these sorts of things, but then later it's actually focused on these sorts of things, and then later it's focused on these sorts of things. That's really interesting. I was thinking of curricula that were a little bit more thought through
Sure.
and not emergent.
I was just trying to make that connection.
No,
to
I
see
think
if that
that's
also could work. Yeah.
I mean, my gut feeling is that I don't know how to make that adversarial agent that actually is gonna, like, it's basically like a teacher, right? It's actually trying to figure out, we're gonna need to focus on this for a little, like a tennis teacher, like your forehand is not good. We're gonna work on that for a little while. I think you need elements of both. I think that's actually really good insight. Thanks.
Thank our speakers again. All right. Thank you, everyone, for hanging around. We now have a lunch break. We're going to be back here at 2 p.m. Feel free to look at the posters anytime, but we'll start up at 2 p.m., at which point we will shepherd you all back into the room and check to make sure everyone is listening. See you at 2.